Okay. Hi, everyone. Once again, let me welcome all of you to this repeated session from yesterday. And the title of this session is Physical Drivers and Climate Implication of Antarctic Sea Ice Variability and Change. And along with me, Dr. Anil Kumar and Dr. Sabu, Sabu. I am Babula Jena from NCPWA. Will be coordinating this session. And today we have back-to-back two slots till 14:40 in UTC time with a duration of 4 hours in a stretch. And we have a very tight schedule today. So since we have a few follow-up sessions, I request the speakers to restrict their talk to 10 minutes, followed by 2 minutes for interaction. And you can ask questions using the Zoom question and answer function. And the posters for this session are available in the SCAR website. And now it is our great pleasure to welcome, invite the first speaker of today's session, Professor Ghosh, and he will be delivering a talk on the influence of sea ice processes, ocean and atmospheric feedbacks on the seasonal cycle of Southern Ocean sea ice. And may I please request Professor Ghosh to start his talk. The floor is yours. I think he's available right now.
Okay, do you see my screen?
Yes, we can see your screen. We can see you well.
So, okay, thank you very much. Thank you very much for the organization of this session and the invitation to present my work. So the subject is the seasonal cycle of sea ice extent. Sorry, could not. I will try again to share my screen because I cannot move the slides. So sorry. Okay, so the sea ice extent as a larger seasonal variability with a maximum of about 20 million square kilometers in winter and a minimum around 4. But this seasonal cycle is so highly asymmetric with a relatively fast retreat and a slow growing season. This has been explained in a recent paper of Roche et al. By the seasonal cycle of insolation with short but intense summer that induce a large retreat and longer period without sun, which corresponds to a longer growing season. But it's not the end of the story. So insolation is dominating the seasonal cycle. That has been demonstrated. But sea ice processes and interaction with the ocean and the atmosphere can also play a role. And to test this role, we have made a series on safety experiments with climate models. There are two groups of experiments. Some experiments are performed with the ocean sea ice model Niño, driven by atmospheric reanalysis ERA 5 at 1/4 of a degree resolution. We will call those experiments later NEMO. And then we also have experiment with NEMO coupled to the regional atmospheric model, Cosmos CLM. We will call those experiments later Paraso. Simulations are started at 2 dates, March 1 and September 1, to see the difference between the growing and the melting season, the initial one. And then we analyze only for 2 years to avoid the too large drift of the system and differences that are more difficult to interpret. So we have made quite a few sensitivity experiments with NEMO, the uncoupled model, and with the coupled model with the atmosphere. Those experiments are devoted to test the role of sea ice thermodynamics, dynamics, exchange with the ocean, and the surface fluxes. For sea ice thermodynamics, we have modified the thermal conductivity of snow and ice. We have divided by a factor 5 or multiplied by a factor 5 with, of course, a very large impact on the sea ice thickness. Those experiments are called thin ice and thick ice, if you understand why. The sea ice dynamics, we have made an experiment in which ice dynamic is switched off, no ice in. Then experiment in which the exchange with the ocean are strongly perturbed. In the first one, we impose a constant mixing of 100 meters all year long. And in the next one, we consider that sea ice has the same salinity as seawater. So it means that there is no brine release during sea ice formation, and there is no release of fresh water when sea ice melts. So the feedbacks between the ocean and sea ice are strongly modified. And in the last one, we have considered that the albedo of snow and ice is equal to the one of the ocean. Plenty of experiments, plenty of results, so hard to present everything. So I'll start with the conclusion. The conclusion is that the timing of the maximum and the minimum are not strongly controlled by the physics of the system. And this is consistent with this recent study of Roach et al. But sea ice physics can play a role on many other elements of the cycle. The advanced season mainly depends on the initial condition in summer, much less about the physics during the season, much more on the physics or the process that occur before the season. The retreat season is different. It's influenced by both the initial condition in winter, or thicker ice melts later, but it is also strongly controlled by the melting rate that vary a lot between the different experiments. And what are the most important elements is the ice dynamics and the ice albedo feedbacks, because they have a large impact on the melting rate. And if you look at the atmospheric coupling, it amplifies the response of the winter ice extent to all the perturbations. So the role of the atmospheric coupling is to amplify the perturbation. So it's positive feedbacks on winter ice extents. So now I'll try to give you some hint about those conclusions. The first one is the seasonal cycle of the ice extent on Niño force and Paraso. So on the left is the coupled model driven by ERA 5. On the right is the coupled model with an interactive atmosphere. So Niño alone, you see that in both experiments, if you start from the same initial condition in March, the growing period is really the same in the two experiments. There is nearly no difference between the experiments between March and August. That could be surprising because the perturbation that we impose is very strong. No ice dynamic, change of a factor 5 of the conductivity, change of the albedo of nearly 80%, and it has no impact on the first growing season. The difference between the experiments start in August, where you see that some experiment has a larger value of the maximum and a longer period where the sea ice extent is large, and some melt very quickly. The second growing season, starting in March, is very different, where now you see that the growing season is depending on the experiment, but it seems that basically the one that has a lot of ice in summer continue to have more ice in spring, in autumn, and in winter. So the initial condition in February, March really play a large role. If they are the same, there are no difference during the growing season. If they are different, there are large differences. But what is going on in winter? The first element is that if you define the onset of significant retreat as the day at which sea ice extent is decreased to 95% of its maximum value, you see that it's strongly related to the maximum ice volume. Why did we use this definition of onset of significant retreat? It's because the maximum is not changing that much. It's more the length of whisker that is changing. And then the speed of the retreat is very different, and it's proportional to the max volume. So it's not very surprising that the initial condition in winter play a large role. Thicker ice melt later. But the difference are also strong between the experiment, even if you start in September. This is the example in coupled mode, where if you start in September, in contrast to the experiment started in March, you see quickly a large divergence of the experiment. This is because of the very different melting rates. Here is the melting rate between the different experiments. Here is an experiment coupled with the atmosphere starting in March. You see that the growing rate, so the growing rate is in winter, it's a negative value. You see that it's very similar in the different experiments, except in the one where we consider that sea ice at the same salinity of seawater, because you have no entrainment of warm water and the growing season can be longer. But except in this experiment, the growing season is very similar and very independent on the physics. But if you see the melting change a lot between the different experiments, and the two extremes are the one in which we consider the albedo of sea ice equal to the one of the ocean, which has a faster melting, it's albose, and the one without dynamics, which has a later and slower melting. So if you look again at the second growing season, you have the feeling from this experiment at the same figure as the one I've shown before, that the second growing season is different from the first one, and it's likely because of the different initial condition. And this is confirmed here, where you could simply look at the maximum extent in the second winter as the minimum extent during the second summer. You see that, indeed, why do you have a change during the growing season? It's mainly because you have a change during the summer. So the advanced season depends on the initial condition in summer. And we have seen already during the first year that it doesn't depend on the physics. So initial condition in summer seems to be a dominant process. I would love to have more time to discuss the atmospheric coupling, because there is a lot of interesting result too. But just to give you a hint, we have computed feedback factors for the coupling between the atmosphere. How do we define those climate factor? We define them as the total response, the response of the system in coupled mode, minus the uncoupled response divided by the coupled response. So a positive value of gamma means that we have a positive feedback. The atmosphere is amplifying the response. A negative value means that we have a negative feedback. Coupling out of the atmosphere tend to damp the perturbation. And you see that in all the experiments, we have a positive feedback factor. If you forget no mass flux at the moment, but you see that the maximum value is when you play with the albedo. So the albedo is a surface element, but the coupling with the atmosphere is very important in the perturbation, because the atmospheric temperature is changing and strongly amplify the response of the system. We also have a very large value in the experiment where we change the salinity of sea ice to put the value equal to the one of seawater. We have in this case a feedback factor which is equal to 5. You must be careful that with the definition that we use here, a feedback factor greater than 1 means that the response in coupled mode has a different sign as the response in uncoupled mode. And this is related to a strong response of the sea ice thickness that has an influence in coupled mode on the sea ice extent, but I will not have the time to give more details about that. So if you come back on the conclusion, you see that really the sea ice physics play a role, maybe not on the maximum or minimum extent, but on the advanced season, on the retreat. On the advanced season, the effect is mainly indirect. So it's not during the advanced season itself that the physics play a role, but on its influence on the initial condition in summer, while during the retreat season, initial condition play a role, but the melting rate is very different between the different experiments.
You have last 1 minute.
Yeah, so I'm finishing here. So and among all the processes, coupling, they all play a role, but ice dynamics and ice albedo feedback are particularly important for the melting. And the atmospheric coupling is also important and can induce some new processes and amplify the one that already occur without coupling. Thank you very much for your attention.
Thanks, Hugh. You have a question. You have a couple of questions. Can you please take up those questions? It is already typed there in question and answer function. Otherwise, let me read out. Did you run multiple simulations of each setup? If just one of each, could there be effects of internal variability? Also, did you look at effects on the atmosphere, like temperature, precipitation, and circulation?
Yes, so we just make one simulation. For the simulation that are uncoupled, that's not at all a problem because the system is not chaotic at all. We have made some tests for the coupled model with the atmosphere, but it's a regional model that is strongly constrained at its boundary, and the internal variability is not negligible, but it's much smaller than the perturbation, which are quite brutal here. So internal variability could play a role, but because of the constraint and the boundary, it's very limited in our setup. It's a regional model, of course, that would be totally different. It would be a global model. We have looked at the temperature, not the precipitation and the circulation, and the temperature is playing this amplifying role, like when you have more sea ice, then you have a cooling, and if you have a cooling, then you have a change in the non-solar fluxes that also influence and tend to amplify the perturbation.
And another question is, what is the role of ocean in feedback? Ocean has large memory, doesn't it feedback overlap different seasons?
Yes, so we have compared the different years, and indeed there is a drift in the system. The second year is different from the first one, and it's not only due to the ocean, but partly. So, for example, in the experiment where we increase the albedo, we have a very different second year, which is much warmer than the first one, because indeed the ocean is increasing in temperature. There is also a buffering effect. For example, if you neglect the heat flux from the ocean, or because you modify the feedback with the ocean during brine release, modify the entrainment, the first year the effect is very strong, but the second year, as the ocean tend to become warmer, the effect can be smaller. So there are a lot of effects that are related to the memory of the system, and it's the reason why we focus on the first 2 years, because if you look at the first year, which is different of the second year, and if you look at equilibrium, it will be also a different year. And the third question is about the predictability. It seems indeed that the winter is more controlled, the growing season is more controlled by the initial condition than the retreat. That summer could indeed, at least if you look at the physics, it's less predictable. You must be careful here that we always have the same atmospheric forcing. So you can also imagine that the maximum can change a lot because you have storms in winter and things like that. Here it's just related to the physics, but indeed the growing season seems very strongly controlled by insolation and the initial condition.
Okay, thanks for this exciting and wonderful talk on impacts of these ocean atmospheric feedbacks. And thanks again for your interesting talk. And next, let me invite Professor Mihir Kumar Das to start his presentation on decadal variability of sea ice extent in the Antarctica. Mihir, are you there? I think he's not responding. So
no, sir, he's not attended the webinar.
Okay. Then we'll go to the next speaker. So now I invite and request the next speaker, Dr. Chia Lin, to start his presentation on impact of atmospheric forcing uncertainty on Antarctic sea ice simulation in CMIP6. Yeah, I think he's there.
Hi, I'm here. But it seems something wrong with my presentation. Sorry.
Yes, you shared your presentation.
Can you see my screen now? Okay, no. So maybe I need to change.
You share your slide. There is in bottom of your screen, there is a share screen button.
Can you see my screen now?
Yeah, in bottom of your screen, there is a green button, share screen.
Yeah.
Yeah. Click on that.
Privacy, sorry. Sorry, can I change another computer maybe? Sorry, I can't share the screen. There is something wrong. Can I will move to the next one? Is it okay? Because I think something wrong with my sharing.
Chia, shall we go to the next presentation? We'll wait till that. Shall we go to the next presentation? If it takes more time.
Yeah, I think so. I will. Can I move to the next one because something wrong with my computer?
Okay, so yeah. Then we are going to the next presentation.
Okay.
So whenever you are ready, just let us know. Yeah. Okay.
Okay.
So may I please invite the next speaker, Professor Rian Fogg, to start his presentation on understanding differences in the 21st century. The 21st century Antarctic sea ice extent reconstructions in the Pacific sector.
Okay, great. Hopefully you can see my screen. So thanks for the session chairs for having me today. I'll be talking about some work that we've been doing lately on comparing some of my reconstructions of sea ice extent with those from paleo records to understand some of the differences between them. So earlier this year, our team published in Nature Climate Change some seasonally resolved sea ice Antarctic sea ice extent reconstructions that cover 5 sectors in Antarctica that are shown in there in the map on the right. As well as the total by the sum of those different sectors. And these are based primarily on observations. You can see in the map there are 30 different stations in the mid-latitudes. We use temperature and pressure records from those and a principal component regression technique where we use various different configurations of that network and perform principal component analysis on them and then regress those principal components in multiple linear regression onto the sea ice extent time series to get the reconstruction. We use different lags as well to indirectly include the effect of the ocean on these reconstructions. And basically by configuring the network size of these stations and also climate index layers that we see listed there as well, we were able to create ensemble reconstructions so that we were able to have different numbers of reconstructions going into these to have an idea of the uncertainty of these reconstructions. So this whole process really removes unwanted noise in the data set and makes the reconstruction represent some of these physical processes, both in the ocean and the atmosphere that you just heard about in whose talk that kind of governs sea ice variability. One of the key factors of our reconstructions was this idea of a regime shift, where in particular in the King Haakon and the Ross and Amundsen Sea, and this is the winter sea ice extent, the recent trends that are positive in growth and ice in these regions, you can see in the black observations, are juxtaposed in our reconstructions by significant declines in the sea ice extent in the early period. So that there's the change in the trend throughout the time where the early and mid 20th century showed declines in sea ice in our reconstructions, and then the observed period with these marked growth. It also means that the observations start in a relative minimum in sea ice in the last century or so. There's also an interesting thing in our reconstructions in the Pacific sector where the Bellingshausen Sea in this region here is offset by the Amundsen Sea, so that there's opposite behavior in these two sectors. In the observations, you see that increases here, declines here, but in the historical reconstructions, you also see growth and decline, opposite behavior in these two sectors. We wanted to see how these compared to some paleo data because there are existing paleo reconstructions that are quite different than ours, because ours are constrained by observations. The paleo reconstructions are usually based on either ocean core sediments or, well, I'll be looking at in this talk, those that are based on ice cores. In the ice core paleo reconstructions, they're using some traces, or usually aerosols that are transported from the ice edge towards the ice core and deposited during the accumulation of that ice core. There's some challenges, though, in comparing paleo versus our reconstructions. In particular, the paleo reconstructions, those that are based on ice cores, typically represent ice conditions in a specific region that don't really align geographically with our sectors. They also typically represent a specific time of the year, like an annual mean or maybe a seasonal mean at the maximum extent of the ice. And so there's time differences as well that make it challenging to compare. Nonetheless, we did try to make some comparisons in our paper when we looked at these things initially. So one of the first things we did is try to look at the geographic sensitivity. And so on the left here are the published correlations of these different paleo records with observations in the time period that those correlations are conducted over. On the right, we now map them to the season and the sectors that we use in our reconstructions. And what you'll see is that there's a lot of sensitivity in this, the correlations drop as you move to different times of the year, different seasons, and different sectors. When you look at our reconstructions, of course, are calibrated specifically to these sectors, and so they perform much higher than what we see even for the published correlations from the paleo records. The challenges, though, come when we compare the paleo with ours. On the right here, this is during the period of satellite observations. The correlations are quite low. They're much lower than we see in our reconstructions with observations, or even the paleo reconstructions with observations in general. And then on the right in the blue, you see the correlations in the early 20th century prior to satellite observations, and those correlations are near zero. There is one exception, and that's in the Weddell Sea sector. Our correlation with the South Orkney fast ice duration record is pretty consistent, suggesting that we have a consistent measure of ice in that area. Though, however, these other ones have differences quite large. It's also not surprising, perhaps, that if ours are different, that there might be differences in the paleo ones. And here, this is the Daladin versus the Thomas and Abram in the Ross Sea, and then the Thomas and Abram in the Bellingshausen Sea. And you can see that there are differences here as well. They may agree a little bit in the satellite period, but as you move into the early 20th century, the differences decline. So there's also differences among the paleo reconstructions as well. Why are these differences? Well, I've kind of hinted at a few of them. All reconstructions are imperfect, so there's obviously error and uncertainty in those that can create differences between these two different methods. There's the time sensitivity issue. I'll look at this a little bit in a bit. Seasonal versus annual means, different months of the year, different times of the year that the paleo records might represent compared to ours. The geographic sensitivity, regional representations of ice in each reconstruction that may not align. I'll definitely look at that and that role. And then just the underlying reconstruction approach. Our reconstructions that we generated from our team are specifically calibrated to observations. Typically in a paleo record, you use a principal component analysis and then some portion of the variability that's related to sea ice. It's not directly always calibrated to the observations in the same way that we create a statistical model that is tied to the observations. So there's differences in the reconstruction approach that can give you large differences in the result in the reconstruction. And of course, there could be many other issues that we won't have time to explore today. So the following stuff I'm going to show in the next slides is preliminary work that we've put together with an undergraduate student, Matter Zrimka, and then Quentin Daladin, who's a co-author on this paper that we submitted to Pages Magazine. It's in review right now. We're trying to understand some more of these differences. And we're focusing on the Pacific sector as a first go, in particular because an observation shown here, there are large increases in the red, statistically significant growth in the sea ice concentration or sea ice extent in the Ross, and declines in the Bellingshausen. So there's a lot of action going on in the satellite observations in that sector. And we're also seeing quite big differences in the paleo and the Maya reconstructions in that area too. On the right, I plot these different reconstructions in the different colors. The observations are in black, and then you can see the various reconstructions here. Abram and Thomas and Abram are both done on ice cores. The Daladin is a little bit more complicated. It's an ice core derived, that a client model that's basically that assimilates paleo records and then is driven by those paleo records. So it's not really like the Thomas and Abram where they're using just an ice core. This is actually from a client model simulation. It gives us more data, but it's still constrained by paleo records. What you'll see here is when we average my reconstructions that are done seasonally to get annual means, and then compare them to these annual means from different reconstructions, there's a lot of differences in interannual variability. So the time sensitivity could be a pretty big factor, but it's hard to know if those differences are just because that different time averaging, or if there are other underlying issues. So that could be one factor. One thing to note here is that there does seem to be some low frequency variability that's similar, decadal scale and longer variability in times of shifts or changes in the mean, despite the fact that the interannual variability is quite low. The similarities in the interannual variability is low. To look at the geographic sensitivity, we can take the various reconstructions and the observations and correlate them with the full spatial sea ice extent field or sea ice concentration field to see what part of that sea ice concentration they represent. So on the top row, we're doing that for the Bellingshausen-Amundsen Seas sector. And on the bottom row, we're doing that for the Ross-Amundsen Sea. And you'll see in the observations, of course, the positive correlations are in those sectors, the Bellingshausen here into the peninsula and the Ross here in the Ross Sea. When you look at the various representations here of the reconstructions, you'll notice that overall, they have a very similar spatial footprint to the observations. Mine, which are calibrated, the observations agree the most naturally. We calibrate it directly to this pattern, this index, this time series. And so they have a good match both in the Ross and in the Bellingshausen. But what you'll notice is that the other ones do actually quite well as well. The Dowden ones match up fairly well. The Thomas and Abram has a really great fit with the observed pattern. The one that may have a little bit different one here is the Abram et al. That maybe has more variability in the Waddell sector than in the Bellingshausen, but nonetheless still captures the general pattern. This suggests that the geographic sensitivity of where these reconstructions are capturing the ice variability is, excuse me, less of an issue than we thought. It's more on other factors that I talked about before. So to look at some of these other ones, here are the running trends of these different reconstructions. The color gives you the magnitude, the sign of the trend. The dots in this plot give you the statistical significance if the trend is different than 0. And one of the factors that you see really clearly is that my reconstructions match the observed. Actually, all of these match the observed very well. But what you'll see in mine is that regime shift. You'll see the positive trends in the Ross and Amundsen Sea shift to negative trends in the early 20th century. In the Bellingshausen, it's opposite. We have observed negative trends in that sector. In my reconstruction, they shift to marked positive trends in the mid 20th century. The paleo reconstructions, whether it's the model version of those from the Dowden paper or Thomas and Abram and all work, you'll see that the signs are basically the same throughout the 20th century as observed. So the negative trends in the Bellingshausen Sea persist throughout the rest of the 20th century and reach some levels of statistical significance throughout that time. In the Ross and Amundsen Sea, the positive trends in the observations stay positive throughout time. And so there's this big discrepancy on the signs and the trends and why they shift. And we're trying to understand more about that now. I showed you previously, it's probably not from the geographic sensitivity where they line up. So there's other things that are governing that variability. What's really interesting, because the Dowden is based on a climate model, you take the paleo data and then run a climate model from that constrained by those paleo observations, we actually can get more than just the sea ice. And so they have the pressure as well, the atmospheric pressure. And what we're showing up here are the trends in the atmospheric pressure from their climate model simulation for the pre-1979 period, the 1979 to the end, and then over the full time period. And what you'll notice, consistent with their reconstruction, maintaining trends of similar sign throughout, is that the pressure trends over Antarctica, even though they're not statistically significant, stay the same sign throughout time. We have done reconstructions earlier in my work on pressure over Antarctica, and in a previous paper, I merged those over Antarctica with the NOAA 20th century analysis to get a merged estimate of pressure variability across the Southern Hemisphere. And what we see with that merged pressure data set, consistent with my reconstructions, is that shift in the pressure trends over Antarctica through time. The decreases that we see in the 1979 to current period that are marked over in the Antarctic continent shift to statistically significant positive trends in the Antarctic in the early part. And so it's this change in the atmospheric circulation that's really influencing the sea ice extent reconstructions, whether that's from a paleo perspective and capturing regional changes in the atmosphere that are driving moisture fluxes and sulfate aerosols and all these things to the ice core site. Or in my case, it's this large scale atmospheric circulation change pattern represented by the mid-latitude pressure and temperature observations that I'm constraining to my reconstruction. And you'll see that shift in the atmospheric circulation. And this is the fundamental thing that we think is driving the differences between my reconstructions that are based on these observations and the paleo ones that are based on some regional measurements of atmospheric conditions or circulation around the Antarctic continent. So for conclusions here, the observations in proxy-based reconstructions have the largest differences in the Pacific sector. Hopefully I showed you a little bit of that here in the talk. What's interesting to us is that the geographic sensitivity of the region where those reconstructions match up seems to play a lesser role in the differences between them. Rather, the reconstruction approach, the fundamental difference is when you're calibrating a model statistically based on observations versus one that you're using paleo records from the Antarctic continent give rise to the differences. And in particular, the references that they make to the changes in the atmospheric circulation throughout the 20th century seem to be the biggest cause of those differences. The proxy reconstructions are regionally constrained by data actually on the Antarctic continent, and they're capturing regional circulation changes driving the flow towards that ice core that do not change throughout the 20th century. Whereas ours that are calibrated by temperature and pressure observations in the mid-latitude give more of a larger scale pattern of variability throughout the southern hemisphere that does change sign, especially over Antarctica, that give rise to the regime shift that we see in our reconstruction. We're doing more climate model simulations to understand some of these differences, including tropical variability and proxy erections from the tropics, to understand if there is this, in fact, shift in what are the strengths and weaknesses of these various products. All right, thank you for your time and attention, and I'll happy to answer any questions that you may have.
Thanks, Trian. There is a question in the chat box. Can the recent decline in sea ice be assumed to natural variability when compared to paleo records?
Yeah, we see that in paleo records that that this falls in the scope of them. Even the record in 2022 that we just set in February seems to be in the scope of historical records from paleo and my reconstructions as well. We're still understanding more of that cause, but tropical variability seems to be an important part in my reconstructions, and there's probably some roles of tropical forcing, changes on like INSO teleconnections, or even short term bursts of tropical energy from convection, like from the Madden-Julian oscillation or other events. So it seems to right now to be consistent with some natural variability, but of course there could be a long-term change that we're still trying to understand.
Okay, there is another question. Would it be possible to combine your reconstruction approach with the proxies?
Yeah, absolutely. We can put it into our model, some proxy data as well, and use that as a way to help to constrain the solution. We would then, be forced to use the resolution of the proxy data. And so one strength of ours is that we can get to higher temporal resolution. We can do seasonal pretty well. We have not been successful in my method at doing monthly or higher resolution, but we would degrade to some degree going in that direction by going to more of an annual or just one season of the year. But absolutely, we could include the paleo records as a predictor in our network and use the same sort of method with that.
Thanks, Rian, for this wonderful talk and answering all the questions. So now I invite, I think Chia is available right now.
Sorry, can I have a try again?
Chia is available right now, so we'll first, please just start your presentation, Chia. Then we'll go for this presentation, yeah.
Oh, sorry. Sorry, please wait a minute. Okay. Can you see my screen? Yeah.
Absolutely, absolutely fine. Yeah.
Finally. Okay. Yeah, I'm Charlene, a postdoc from UC Leuven. today my topic is about the impact of the atmospheric forcing authorities on the sea ice simulations. Arctic and Antarctic has experienced dramatic changes during recent decades. People are very clear about what kind of processes are at play, from the sea ice dynamics to the atmospheric and ocean processes. And we model groups are also want to simulate and predict this kind of changes because they are very important for the air-sea interactions, for the circulation and the stratification changes, and also for our human activities there. Before moving to my topic, I hope to introduce a bit about our recently developed sea ice tool here. It's a newly developed sea ice tool for the large-scale sea ice simulations, and we want to do some benefits to the model groups who want to quantify the bias in the sea ice simulations and who want to track the performance across the different model versions. It is open access on GitHub. Here's a link to it. The main idea is that you need to prepare the model output, and we have two sets of observational data sets for many variables. And the CS evaluation tool will do the interpolation, calculation, and plot for you. In the end, we will provide the CS matrix, including many aspects of the sea ice simulations, from the concentration, extent, age, to the ice drift, and also thickness. And we'll also provide some special maps and time series diagrams to support your understanding of the model ability in produce the sea ice properties here. And we apply this CS tool to evaluate the simulations in the CMIP6 OMIP simulations, in CMIP6 OMIP. And here is the typical output from our CS tool. And CMIP6 OMIP simulations are ocean general circulation model forced by the atmospheric forcing. There are two forcings here. Model C here is meaning the ocean general circulation model is forced by the CO2, and the J here is meaning they are forced by the GI55. They are called OMIP2 simulations, and the forced by the CO2 is called the OMIP1 simulations. From this picture, we can see that the OMIP2 simulations are much improved here because in our matrix, it is model bias to the observation, and if it's lower values, it means the better scale here. So there are improved simulations in both hemispheres for the mean state standard deviation, like the variability, and the trend for the sea ice concentration simulations. So we want to understand what processes are important here. The first column here is the ice concentration from the observation, and the others are from other model bias. The first one is from OMIP1, and this is from OMIP2, and these are the OMIP2 and OMIP1 differences here. We can see for the Arctic summer, there's a negative bias here in the OMIP1 simulations, but it's not existing in the OMIP2 simulations. And for the Arctic winter, the improvements are very small here. For the Antarctic, there are some small improvements in the coastal regions of the West Wetter Sea and the Amundsen Sea, these regions, but it's very small. But for the Antarctic winter, the positive bias here is reduced mostly from 70 to 180 degrees here. So we did the sea ice concentrated budget to diagnose which part is more important for these improvements. These are the ice concentration tendency due to thermodynamic and dynamic processes. The first row is from the OMIP1 simulation, and the second is the differences between OMIP2 and OMIP1. We can find that the increased ice concentration in OMIP2 simulations are mostly related to the thermodynamic processes here. And for the winter, the decreased ice concentration in the around this region of the Antarctic is mostly related to the dynamic processes here. Then we move to the surface heat flux and the wind streams on the sea ice. We can find that for the Arctic summer, this pattern is very similar to this heat flux changes. And this is the net heat flux changes. There's a negative bias here, negative differences here. This is mostly can be traced back to the differences in the shortwave radiation, these negative differences here. So our conclusion is that the decreased downward shallow radiation flux contribute to the increased ice concentration in the OMIP2 simulations and contribute to the improvements in the summer Arctic there. For the Antarctic winter, it's mostly related to the decreased wind stress here and to the dynamic processes here. And we also have a look at the ice drift metric. We can find that both the ice drift magnitude and the direction are also improved in OMIP2 simulations here and here. And the magnitude is measured by the mean kinetic energy, and the direction is on the vector correlation at each grade here. We also want to identify the processes at play, and these are the pictures of the monthly mean and the spatial average, the MKE. The first one is MKE, and also we consider the ice concentration, ice thickness, and the wind stress. How to do the spatial average? We divided these regions into two regions. There are ice edge regions with concentration smaller than 0.8 with free ice drift, and also the interior region with ice concentrations larger than 0.8. Here, the blue color is from the observation, and the green is from OMIP2 simulation, and the yellow is from the OMIP1 simulation. We can find the most obvious improvements is on the exterior region in CIS edge region. That the positive bias here is mostly reduced from November to April here. And but for the concentration and the thickness, there's no differences between OMIP1 and OMIP2. So the reduced MKE here is mostly related to the reduced surface wind stress here. So it means that for the Arctic exterior region, the improved wind stress can improve the simulations of the ice drift magnitude here. And there are also some improvements in the September. It's mostly related to the increased concentration and the thickness here. For the Antarctic, the improvements are much smaller, and there are some improvements in April and August for the ice edge regions. For the April, it's mostly related to the increased concentration and thickness, but for the August, it's mostly related to the wind stress. And some improvements in the March and April, it's mostly related to the increased concentration and thickness here. But these improvements are much smaller. We also do the vector correlation coefficients between the modeled ice drift and the Kumar observational datasets. The first row is between the modeled ice drift and the Kumar datasets, their coefficients, and the second row is a modeled ice drift and the surface wind stress, their correlation coefficients. And we can find that for both Arctic and Antarctic, the improved surface wind stress here can improve the ice vector simulations in many regions here. Then we come to the conclusion here, like we encourage you to have a look at the CS tool, especially for the model groups. It can help you manage your CS model. And in our simulations, the improved ice concentration is mostly related to the improved downward shallow radiation flux in the Arctic summer in the interior region. And for the Antarctic winter, there are improvements related to the improved wind stress there. And the ice drift, for the ice drift magnitude simulations, the decreased surface wind stress in the Arctic ice edge region can improve these ice drift simulations here. And also the improved wind stress can improve the ice vector direction simulations there. Our conclusion is that more attention can be paid to the radiation flux and the wind fields in the analysis datasets for better CIS simulations. Thank you. Hi.
Thanks, Jia, for this excellent talk on uncertainty Antarctic CIS simulation. And there is no question in the chat box. So we'll move to the next speaker. Now, may I please invite the next speaker, Mr. Arnab Sen, to start his presentation on studying tropical Antarctic teleconnection using linear response method. Yeah, please start your presentation.
Is my screen visible?
Yes, it is visible, and just make it to full screen mode.
Yeah. So hello everyone. I am Arnav Sen. So I am now going to talk about the tropical Antarctic teleconnection using linear response method. So over the modern satellite era, Antarctica has experienced substantial climate change. And the factors responsible for such change includes increased emissions of greenhouse gases, stratospheric ozone loss, changes of Southern Annular Mode, etc. However, the seasonality and spatial heterogeneity of the observed changes cannot fully be explained by those factors. The tropical polar teleconnection has found to be an important factor in explaining the zonal asymmetric change. It has been found that the teleconnections can originate from tropical oceans and their combined impact on Antarctic climate can be quite substantial. So now I am going to talk about the teleconnection between the Indian Ocean Dipole and Antarctica. So Indian Ocean Dipole is an anomalous state of the ocean atmosphere system. So the positive phase of Indian Ocean Dipole is characterized by anomalous cool sea surface in the eastern equatorial Indian Ocean and anomalous warm sea surface in the western equatorial Indian Ocean. And vice versa can be seen for the negative phase. And the peak season for Indian Ocean Dipole is between September to November. And in our study, the positive IOD years were quantified using the dipole mode index as suggested in Saji et al. 1999. And positive IOD years are those in which the mean HO and DMI were higher than 1 standard deviation. So the method that we have used in our study is a linear response method, which has been designed by Dev et al. In 2020. So using the linear response method, the signal S can be expressed as the weighted sum of the previous forcing, and mathematically it can be expressed by the equations shown here. Here S is the signal which is nothing but the daily geopotential height anomaly at the 250 hectopascal over the extratropics of the southern hemisphere, and F is the forcing which is nothing but the precipitation anomaly over the tropical Indian Ocean. And for the forcing time series, we have computed a similarity metric, which is nothing but the inner product between the composite map of IOD precipitation anomaly and the daily precipitation anomaly map. So ultimately, the similarity metric becomes the daily time series for SON, and the higher values of the metric represents the higher similarity. So here, if you see in the in figure A, we have prepared the composite of daily CMAP precipitation anomaly for the positive IOD years between 1950. And here you can see over the Indian Ocean within the green box, you can see the IOD precipitation pattern. And over the equatorial Pacific, you can see a large area which is containing a positive precipitation anomaly, which is actually associated to ENSO. So what is our goal? Our goal is to quantify the role of the precipitation anomaly that is present over Indian Ocean and to remove the precipitation anomaly that is associated to ENSO. So what is our method is doing? Our method is trying to find out the days over which this precipitation pattern was there, and it is preparing our forcing. And ultimately, when we are preparing our forcing and we prepare the similarity metric, so ultimately when we are preparing the composite of daily precipitation anomaly over days, when the similarity metric were within the upper quartile, we can see over the Indian Ocean only the IOD precipitation pattern is there, and we have successfully removed the ENSO precipitation pattern from the tropical Pacific. So now we have prepared the extratropical response to IOD. Here you can see in figure A is the step response function for the anomalous 250 hectopascal geopotential height. And in figure B is the composite map of anomalous 250 hectopascal geopotential height during the SON of the positive IOD years between 1980 and 2050. If you see in figure A, you can see the extratropical Rossby wave response, and you can see the Rossby wave is starting its propagation from the Indian Ocean, and then it is gradually moving, it is reaching in the Pacific sector and in the Atlantic sector as well. And as the anomaly centers are located in the sea ice anomaly region, so it is expected that these anomaly regions will have significant impact on the Antarctic sea ice. So now what we did in our next step is that we choose a set of CMIP-5 models and we prepare the similar extratropical response, and we analyze the model's performance in details. So in order to identify the model performance or the Rossby wave propagation, we actually check the Rossby waveguide structure in the extratropics by quantifying the stationary Rossby wave number following Hoskins and Ambridge 1993 and Dawson et al. 2011. So here you can see the Rossby wave which is traveling, which is actually following the waveguide. And in this Rossby waveguide structure, Rossby wave number 2, 3, and 4 are really important. So we also prepared this Rossby waveguide structure for a set of CMIP-5 models, and we also quantified the biases. And I will talk about the CMIP-5 models in my later slides. Another important aspect is the IOD precipitation pattern. So if we see our forcing, if we see the composite of precipitation anomaly for the IOD years, we can see during the time of IOD years, there is a positive precipitation anomaly region at the west, and there is a region of negative precipitation anomaly at the east. So overall, it is making an east-west kind of pattern. However, when we checked this composite of precipitation anomaly pattern in some of the CIMIC-5 models, we have seen this. We have seen that this positive precipitation region is actually shifted to the north, and the negative precipitation anomaly region is shifted to the south. So thus making it a north-south kind of pattern. So in order to quantify bias in the IOD precipitation pattern, we have calculated two ratios. One is the east-west ratio, another is the north-south ratio. So the east-west ratio is nothing but the ratio between the number of grid points containing the positive anomaly values in the region at the left, and the number of grid points containing the negative anomaly value in the region at the right. So the bias in the east-west ratio is the east-west ratio from observation and east-west ratio for each of the model. And then we also similarly we calculated the north-south ratio. So the north-south ratio is nothing but the ratio between the number of grid points containing the positive anomaly in the box at the top and the number of grid points containing negative anomaly values at the bottom. So the bias in north-south ratio is the north-south ratio for observation minus north-south ratio for the model. And the total bias in IOD precipitation pattern is the sum of the bias in east-west ratio and north-south ratio. So in our study, we have considered the 19 CIMIC-5 models, which actually correctly simulated the peak season of IOD as mentioned in McKenna et al. 2020. And we classified the model into 4 groups in A, B, C, D, in terms of how they are representing the Rossby waveguide structure and IOD precipitation pattern. And we can see the class A models, they have good representation of waveguide structure and precipitation pattern. For the class B model, the waveguide structure is good, but the precipitation pattern is poor. For the class C model, their waveguide structure is bad, but they have good representation of precipitation pattern. And for class D models, both are poorly represented. So now we have produced the extratropical response at 250 hectopascal in all class of the model. You can see in class A model, when the Rossby waveguide structure and the precipitation pattern is well simulated, these class A models have actually captured the response quite well, and the anomaly centers are properly located, as we can see in the observation. For the class B models, the Rossby waveguide structure was good, but the precipitation pattern was not well simulated. Here we can see the Rossby wave response, but the anomaly centers are out of phase, as we can see from the observation. For the class C models, the Rossby waveguide structure was poorly simulated, even though the precipitation pattern was good. So this model couldn't get any Rossby wave pattern, because if there is error in waveguide structure, the waves generated in the tropics, it moved in the different direction. And for the class D models, as the both waveguide and the precipitation pattern was bad, so it couldn't get any pattern. So here in the at the end, we can say that linear response method is a powerful tool to analyze the tropical Antarctic teleconnection. And the drivers of Antarctic climate, they are superimposed on one another. So using linear response method, it is possible to isolate and quantify the role of a particular forcing. That I have shown that in our forcing, we have successfully eliminated the insulated precipitation, and we only quantified the role of the IOD precipitation. And there is large intermodal difference in the teleconnection pattern in CIMIC-5 models. However, the performance of the CIMIC-5 models in terms of capturing the teleconnection pattern depends on how they are simulating the waveguide structure and IOD precipitation pattern. However, it seems the waveguide structure is more important than the tropical forcing pattern. So my future work includes that is to evaluate the CIMIC-6 models, that whether there is really bias in the waveguide structure and also the precipitation pattern. And if the bias is there, so how they are actually producing the extratropical response of this teleconnection pattern. So here are the references, and thank you very much for your kind attention. If you want to contact me later, so you can contact me in Twitter and my email ID as well. So thank you very much.
Thanks, Anil, for presenting your very exciting research work on polar tropics teleconnection. There is a question for you. Does the IOD affect zonal wave 3 over Antarctica?
Yes, I think so. So like if you see our Rossby wave response, so it is kind of like zonal wave 3 pattern, which is actually generating. So actually, I think from Indian Ocean Dipole, zonal wave 3 pattern can be generated, and it can affect the sea ice as well.
Okay, Anil. Okay, thank you.
Thank you.
So now I would like to invite Dr. Yu Seok Chung to start his presentation on diagnosing opposing Antarctic sea ice trends in satellite observations and model projections.
And thank you, Chairman. Hello, everyone. I'm Lee-Seok Chung from Korea Polar Research Institute. Today, I'm going to talk about the potential causes responsible for model observation discrepancy in Antarctic sea ice trends. And this study was conducted together with Dr. Sung-Jun Kim and colleagues from ISSB, NOAA AOML, and University of Hawaii. As is shown in ISSB reports, while climate models are able to reproduce the observed decrease in Arctic sea ice, they fail to capture slight increase in Antarctic sea ice over the satellite period. And assuming that satellite observations are accurate, the main cause of the model observation discrepancy is either incorrect force response in model simulation or internal variability in observed changes. It is also possible that both factors are responsible for the discrepancy. However, considering short satellite record, the attribution may not be straightforward if the Antarctic sea ice exhibit distinct multidecadal variability. Also, it is difficult to separate observed changes in over relatively short period into external force response and internal variability component. To overcome these obstacles, we used relatively longer sea surface temperature record as a proxy for Antarctic sea ice, and along with multiple large ensembles of model simulation based on the fact that observed Antarctic sea expansion was accompanied by overall cooling of sea surface temperature in the Southern Ocean. So this slide compares the observed and model simulated trend in sea ice extent and Southern Ocean mean SST. So here the box whisker plot shows the distribution of model simulated trend with dark blue color representing trends over 1979 to 2014 and green color 1950 to 1978. And the observed trend over 1979 to 2014 represented by the red line indicate sea ice expansion and concurrent Southern Ocean cooling. However, as shown in the first column tagged as HIST, the models analyzed in this study failed to capture these changes. To determine whether this model's failure is due to insufficient number of ensemble members, the trends are computed using all possible overlapping 36-year segments of the pre-industrial control simulation output. And the second column tagged as PI shows resulting distributions. And in this case, observed trends lie within the range simulated by the climate models in the absence of external forcings. Then we adjusted this distribution by adding ensemble mean trends over 1979 to 2014 for each model. And the adjusted distribution indicate that adding the force response causes most models to fail in capturing the observed trend. So this implies that the model's failure is due to either overestimated force response or underestimated internal variability in simulation rather than insufficient ensemble size. Some previous studies attributed this potential overestimation or incorrect sign of the model simulated force response mainly to missing fractional fluxes from sub-ice shelf melting. Others also point out the stronger global warming response in simulation as a cause. Although I don't have time to go into detail, but the model observation discrepancy in global warming response is caused in part by observed tropical variability. Meanwhile, the original line denotes the observed trend over 1950 to 1978. It indicates Southern Ocean warming, which implies sea ice decrease over that period. In this case, models capture this warming trend, although they underestimate. To explain whether the observed sea ice expansion can be explained by internal variability, the temporal evolution of observed sea ice anomalies compared with model simulation. In this figure, the red line denotes observed time series, and other line represent model simulated ensemble changes. And this figure shows that the model simulation exhibits largely monotonic sea ice decrease over time. In contrast, observation indicates substantial variability. As shown in the previous slide, the continuous satellite observation indicates slight increase in sea ice over 1979 to 2014. However, this expansion was virtually canceled out by precipitous decline of the subsequent years. And also, the pre-1979 observation indicate large sea ice decrease in the 1970s. And Nimbus 1 satellite observation for September 1964, represented by the red dot, further suggests the presence of multidecadal variability in Antarctic sea ice. Although the observed short-term trend do not always agree with model simulations, the sign of the longer-term change doesn't appear to completely disagree with the model simulation. However, due to the absence of continuous satellite observation before 1979, we cannot quantify the CI change over a much longer period. So we turn to the SS time series. Here again, red line denotes observed time series. Here we can see the cooling trend over 1979 to 2014. And this cooling trend was followed by warm anomaly in recent years and preceded by warming trend over the previous period. And the sign of SS change over the entire analysis period is broadly consistent between observation and model simulation. So these results support the argument that the observed Antarctic CS expansion is related in large part internal variability. This slide shows special pattern of observed and multimodal mean trends over 1979 to 2014. The multimodal mean trends for the multimodal trend, the spatially coherent sea ice decrease and ocean surface warming in the Southern Oceans are observed together with overwarming in other regions. In contrast, in the observation, the overall expansion of sea ice and ocean surface cooling in the Southern Oceans are accompanied by marked cooling in the central to eastern tropical Pacific and substantial warming in the northwest, southwest Pacific, and north Atlantic. So this special pattern implies the potential connection of the change in the Southern Ocean to tropical climate variability. So assuming the linear trend over 1950 to 2020 represents the external force response, on the first component of SA change is estimated by a linear detrending. Here, red line denotes detrended Southern Ocean mean time series for observation. Here we can see the presence of multi-decadal variability with opposing trend between 1950 to 1978 and 1979 to 2014. In the panel, the blue line denotes time series of Atlantic multidecadal variability with the sign reversed, and green lines time series of interdecadal Pacific Oscillation. And comparison of the time series indicate that this indicates some connection of multidecadal variability of Southern Ocean SST to both IPO and AMB. And lower panel shows the correlation coefficients of the trend SST time series with corresponding Southern Ocean mean time series. And the figure shows that in addition to the Southern Ocean, high correlations observed in the tropical Pacific and North Atlantic confirming these connections. So we computed the regression coefficients of SS change against AMB and IPO, and the top two panels shows resulting special pattern of regression coefficients. Meanwhile, the externally forced response may not be linear over time, so we also identified on first component of CIS changes and SS changes by subtracting model simulated ensemble mean change from the observation for CSM2, CANDSM5, and NORCPM1. The other 6 panels shows resulting regression coefficients. But although there's some discrepancy between methods and between models, in our cases, the multidecadal variability of Southern Ocean SST is closely linked to both AMB and IPO. To determine whether similar relationship hold in model simulation, we also computed regression coefficients of SS change against AMB and IPO using pre-industrial control simulation for subset of models. And panels on the left-hand side shows regression coefficient against AMB and right-hand side against IPO. The regression coefficients against AMB exhibit substantial intermodal discrepancies in terms of spatial pattern and magnitude. So this implies that the AMB signal may not be robust over the Southern Ocean, or models have deficiencies in representing these teleconnection processes associated with AMB. In contrast, the models appear to reasonably capture this connection of Southern Ocean SSC to IPO. However, unlike in observation, the regression coefficient in the central to eastern tropical Pacific is much stronger than those over the Southern Ocean. And also, the IPO exerts much weaker influence in the Southern Ocean compared to the observation. So to assess this discrepancy more quantitatively, we computed asset trend over 1979 to 2014, which is congruent to observed IPO and AMB trend using multiple linear regression coefficients. And upper panel shows the congruent asset trend for observation, and the panel shows that the teleconnection associated with AMB and IPO explains a substantial portion of the observed cooling trend of the Southern Ocean. And lower panel shows multimodal mean congruent trend. Here, the models capture the broad picture seen in the observation. However, the magnitude is distantly smaller over the Southern Ocean compared to observation. And also, In some cases, sign is not consistent with the observation. So the externally forced response dominates over internal variability in simulation, contributing to model observation discrepancy. Meanwhile, the phase of IPO shifted from positive to negative during the period of 1979-2014. So we examined whether the IPO phase shift can explain the power of the observed change over that period using idealized coupled model SS forcing experiment. And this panel shows response of sea ice concentration and SS to positive to negative IPO phase shift. As you can see, this IPO phase shift resulted in overall increase in sea ice concentration and ocean surface cooling in the Southern Ocean. And we also examined whether opposing trend between 1950 to 1978 and 1979-2014 can be explained by internal variability by analyzing pacemaker experiment in which the observed SS anomaly in the equatorial Eastern Pacific were assimilated in a coupled model simulation. And upper panel shows time series of sea ice extent and lower panel is Southern Ocean mean SST. So although there's year-to-year variability is substantial and long-term trends are weak, but this model simulation broadly captured the opposing trend between the two periods, so highlighting the role of internal variability. So to summarize, our study shows that observed Antarctic sea ice expansion is related in large part to decadal variability in the Southern Ocean, which is closely linked to tropical climate variability. The tropical teleconnection to the Southern Ocean is, however, weaker in model simulation compared in observations. So the external force response dominates in simulation, contributing to model observation discrepancy. So that's all I have today. Thank you for your attention.
Thanks, Yusiok, for an excellent work investigating the opposing trends of sea ice from both observation and model projections. And you have shown that the Southern Ocean sea surface cooling and ice expansion, it is linked to internal ocean variability in the tropics. So it's very interesting. Thanks, Yusiok. And next speaker is Ms. Maren Elizabeth Richter. The title of her presentation is Variability in Fast Ice Thickness in McMurdo Sound over 25 years and its connection with the ocean, ice shelf, and atmosphere. I request our IT team to play the pre-recorded video.
Hello, my name is Maren Richter, and I will be talking about variability in fast ice thickness in McMurdo Sound and connections to ocean ice shelf and atmosphere. I am a PhD student at the University of Otago and funded by the University of Otago, Antarctica, New Zealand and Niño. McMurdo Sound is located in the western Ross Sea, as shown by the red dot over here. It is not a true sound, as it is connected via the McMurdo ice shelf cavity to the much larger Ross ice shelf. From underneath that cavity, supercooled ocean water can flow out into the sound and influences the fast ice there. Ross Island is located to the east and the Victoria Land coast to the west. Each year, seasonally land-fast sea ice forms in a crescent in McMurdo Sound and breaks out again. Between 1996 and 2020, we have had a sea ice mass balance station deployed in various locations in the Eastern Sound, shown by the cyan dots over here. Between 1986 and 2013, manual measurements of sea ice thickness were also made at the sea ice runway that is operated by the US Antarctic program, shown by the orange star over here. You can see the years in which we have had a sea ice mass balance station deployed in the cyan numbers over here, and between 2000 and 2006, giant icebergs were located at the mouth of McMurdo Sound, which caused the fast ice there to become multi-year fast ice and not break out until 2011. The main component of our mass balance station is a thermistor probe, which measures sea ice and ocean temperature at predefined intervals and sends data back to New Zealand. To get sea ice ocean interface from temperature data, you can look at the top panel here, which shows the depth and time with the colors being temperature. The ocean is isothermal at its freezing point, and the ice gets colder as closer you get towards the surface. The black dots show the interface that we get from the temperature data, which matches very well interfaces that were measured manually, shown in the crosses and stars down here. The purple crosses here that show up below the ice-ocean interface measure the sub-ice plate layer thickness, which I will go into more on the next slide. These sub-ice plated layers are at the ocean temperature, and the temperature in that varies with the ocean temperature. You can see this in the slide below, which shows the vertical gradient in temperature, which varies in the ice but does not vary in the ocean or the sub-ice plated layer. Normally, ice will grow through heat loss to the atmosphere and will form columnar ice, shown over here. However, in areas where we have a supercooled water column, frazzle ice can form in the water, rise up forming platelets, and these then accumulate underneath existing ice, forming a friable sub-ice platelet layer which has large interstices filled with ocean water, as shown on the right over here. When ice grows through heat loss to the atmosphere, it then grows into these interstices of platelets which have grown to heat loss to the ocean. This is called incorporated platelet ice, and we can see a transition from columnar to incorporated platelet ice by taking sea ice cores. Our sea ice probes only measure the consolidated sea ice thickness, as do our manual measurements. To get interannual variability from a fast ice record, you need a long fast ice record in a location where it preferably has not changed very much over the course of that record. This is the case in McMurdo Sound, where fast ice has been very stable since the earliest recordings in 1902. Previous studies of the fast ice in McMurdo Sound have looked at the extent and break-up of it and its correlation with storminess. Most study of sea ice around Antarctica and its correlation with different drivers look at sea ice extent and concentration of pack ice, since this is easier to derive from remote sensing. Some studies of fast ice do, however, exist from the South Orkney Islands, Atka Bay, Lutzeholm Bay, and from near Davies Station, which are shown in the coloured dots over here. However, most of these only have short time periods in which they study the ice or do not look at thickness. We will study sea ice thickness correlations with atmospheric heat flux, which we will take as temperature and wind speed, oceanic heat flux, which we will look at via the plated ice transition in McMurdo Sound, freezing degree days, the date of fast ice formation, which is influenced by storminess during winter, which can blow out newly formed ice when it is not thick enough yet, and different climate indices, El Niño Southern Oscillation, Southern Annular Mode, Interdecadal Pacific Oscillation, and Atlantic Multidecadal Oscillation, which have all been shown to influence pack ice in this area. We will look at a time series here of monthly mean sea ice thickness anomalies in centimeters versus years in which the data was collected. The colors are the different months, and open circles show data collected by Kim et al. At the beginning of our time period and by our sea ice mass balance station more towards the end of our time series. The grayed out area is the time in which they were heavily influenced by icebergs in the Sound. The next plot down shows mean annual freezing degree day anomaly and mean annual air temperature anomaly, the mean annual wind speed anomaly for the total zonal and meridional components, and normalized climate indices at the bottom. From a first look at this, there are no obvious correlations between monthly mean anomalies of thickness and annual mean anomalies of the different drivers. So we will look at monthly and seasonally averaged anomalies of the drivers with different lags relative to their monthly mean fast ice thickness. We will look at linear correlations between a driver and thickness in a specific month, in this example looking at November sea ice thickness versus the depth of the plated ice transition. So the more negative this number here is, the further down in the core plated ice first occurs, and the more negative this number over here is, the thicker the sea ice was in November. We see a strong correlation with an R-squared value of 61% and a p-value that shows that this is significant at the 1% margin. It is very counterintuitive, however, that in years with platelet ice high up in the sea ice column, the ice was thinner. So other things might be going on here. Looking at monthly lag correlations, I will show an example for the modified storm index, which is calculated from temperature and pressure anomalies and is related to winter southerly storms coming through and blowing ice out of McMurdo Sound. The top panel shows data from our CS mass balance station. Each row is a month in which we are studying the sea ice thickness, and each column is the number of months relative to this that our driver is lagged. So for example, for August sea ice thickness, we are looking here at August MSI, July MSI, June MSI, and so on and so forth. Colors show the R-squared value, and the stippling shows significance at 5%. We can see for this that the top panel, which shows data only from our sims, and the bottom panel, which shows the entire time series, that the correlation and the significance decreases with increasing length of time series. So for the entire time series, August thickness is correlated with July MSI, and November thickness is correlated with June MSI only. This makes sense, as June and July are the last 2 months in which fast ice regularly gets blown out of McMurdo Sound and can thus delay fast ice formation and thus thickness. Conclusions are that the best explanatory variables for fast ice thickness in McMurdo Sound are the depth of the plated ice transition for November sea ice thickness, the June to July modified storm index, autumn through winter atmospheric temperature, summer through autumn SAM, IPO, and ENSO combined with SAM, though those are weak correlations only and we did not show them here. Caveats are that there is a spatial component in the data, a mix of methods to derive thicknesses. The time series is only just over 30 years long, and there are issues with the meteorological data, especially around orographic steering of wind. Future steps are to look at freezing dates from remote sensing and to investigate forcing mechanisms, and look at the ocean and possibly combine this with modeling. If you know of any study comparing thickness of fast ice with climate or meteorological variables, please let me know. Thank you very much.
Thanks, Marian, for this amazing work on the southernmost navigable water body of Antarctica. I would request the audience, if you have any questions, she is available, she can answer you, she can respond to you. Otherwise, we'll move to the next speaker. Let me invite the next speaker, Dr. Stephanie Art, who will be talking about the evolution of an ice regime drifting through the Weddell Sea. Dr. Stephen Art, if you are available, can you please start your presentation? Yes, yeah.
Yeah. All right. Can you see my screen? And
yes.
Mode. Perfect.
Yes,
yeah. Thanks a lot for the session, to the session's convener to let me speak here about my most recent work. And this is also still, I must admit, still work in progress on recent expedition data from the Weddell Sea. But first of all, just to introduce you into the topic of the Antarctic sea ice in general, I mean, we had already several talks talking about this evolution of the sea ice extent. And this is again exactly the topic also of that talk in terms of process understanding, because we all know that we are currently in a phase where we have a really kind of decrease in sea ice extent around Antarctica. However, overall, looking at the whole time series from the end of the 1970s, we do see, or we do say that since the last IPCC, we do not observe any significant trend in any direction. However, the models, and this is when we talk about the Antarctic sea ice paradox, the models say that we are in a phase of strong decreasing sea ice extent, what we are not observing yet. And it's of course then the big aim to understand this mismatch between observations and models, and therefore, yeah, I'm happy to contribute to that understanding by several studies on in situ observation, and therefore the main objective of that talk is how do snow and ice properties change in general over the course of the year in terms of get a better understanding of internal processes in terms of the sea ice mass budget on the one hand, but especially also a better understanding on the sea ice growth processes, especially on Antarctic sea ice, as they are kind of special, as I will just talk in a couple of minutes about. So those are the objectives. And to tackle those objectives, I had again the possibility to join several expeditions to the Weddell Sea, and you see on the left panel all expeditions we carried out in the towards the Weddell Sea in the last couple of years or even decades by now. And now the most or one of the most recent ones with our German icebreaker Polarstern is the PS 124 expedition. It was last year in the beginning of the year to the Eastern Weddell Sea. And during that expedition, we carried out our kind of normal sea ice program. And I just want to give you an overview on the general kind of numbers and statistics. So we carried out about 17 ice stations, really successful, and came up here with a mean sea ice thickness for the southeastern Weddell Sea of about 1.8 meters of the sea ice thickness and about 35 centimeters of snow. So this is kind of usual, and also what we kind of compared in previous expeditions in previous years in a similar area. So there's again, as we observed in previous years, also for the northwestern Weddell Sea, we cannot see any significant trend here. However, as mentioned before, it's all when we talked about Antarctic sea ice and especially the snow cover on top, it's not only about the thickness, but it's really about the processes at the snow ice interface. And therefore, a big part of my work became especially really looking into those processes. And this is then in winter, we have this heavy snow load pushing the snow ice interface more and more below the water level, causing a flooding of the snow ice interface, and then therefore a refreezing, in which is forming then snow ice. And in summer, on the other hand, we have internal snow melt processes where then the snow melt water percolates downwards, kind of collecting at the snow ice interface and is refreezing there, forming so-called superimposed ice. And both processes lead to an additional sea ice growth at the top of the sea ice, and therefore it's of course also something that kind of prevents the ice to melt, so to say. So what we are doing for that is when we are in the field, we take a lot of ice cores, on the one hand for the biologic analysis, but also for especially the analysis of these ice growth processes, which we then do on the one hand really in the lab, looking at the ice structure in terms of the crystal structure. This is what you can see here in the images, and then here in the results. And now in the middle panel, so to say, you see all ice cores that we took and then really classified for the different ice crystal types. And it's also, again, it's kind of expected what we also saw before, and then in addition, because this is really just like on a qualitatively or more on a quantitatively level, we then do in addition ice core analysis for isotopes and salinity, because the combination of both really allows us then to distinguish between ice that was growing really from the ocean, ice that was formed from snow only, and ice that was formed from this flooded, refrozen snow called snow ice. And this is where you see here on the left panel, just all measurements for the salinity and for the isotopic analysis. And then now in the next figure, you see again for all ice stations that we did now, sorted by longitude. You see on the left panel the sea ice thickness, then in panel B the snow depth, then the freeboard, and then the layers thickness of the different derived layers. And what you can see is that we had a lot of snow ice, because we also, as you can see in the freeboard, we had a lot of negative freeboards. However, so a lot of flooding. However, we did not observe any superimposed ice. So this was really also again typical for the southeastern Weddell Sea, so also something that we expected, but still something that is really completely different to what we observe in the northwestern Weddell Sea. So we had a mean snow ice layer thickness of around 18 centimeters, ranging from 0 up to 58 centimeters, which was quite a lot. Again, I also did the typical snowpack analysis, where we also looked really into the different snow grain types and so on and so forth. And also here, we hardly observed any typical snow metamorphism processes. And as I mentioned before, we didn't observe any superimposed ice, because this was really, the snowpack was really characterized by a lot of flooding and therefore slush. And all the other parts or kind of crystals that were there were again kind of typical and usual as things that we observed before. So as we now, of course, as you know, we can't be always in the field, and especially we cannot cover the whole seasonal cycle. Therefore, also during that expedition, we deployed several of our snow buoys. You can see here on the right-hand side a snow buoy. It measures actually the distance from the sensor to the surface, and which you can then translate into snow accumulation. We deployed 3 of those, but unfortunately 2 died pretty soon due to crashing into the ice shelf, or just like crashing and enriching of the ice. But luckily, one of the buoys survived it, and you can see here now on the left panel the drift trajectory of the buoy that survived the summer melt completely, and then drifted through the Weddell Sea towards the northwestern part of the Weddell Sea. And this then, this buoy allows us actually to describe then the snow depth, of course, along that, or the snow accumulation, as I mentioned, along that trajectory. But now in that specific case, we have been then, in addition, in the lucky position that over the course of the last year, I was then asked to join the Endurance 22 expedition, an expedition that was meant to look for the wreck of the Endurance. And when I heard about it, and when I then saw where the expedition is meant to take place, it fitted actually pretty well to where the snow buoy that I was deploying the year before, or like in the season before in the southeastern Weddell Sea, it fitted pretty well with the same time frame. And what you can see here now is again the drift trajectory of the buoy, and then in blue where the buoy was in February, March, and then in red, this red box is the actually the location where we looked for the Endurance wreck. And it actually really fitted just perfectly. So we had basically the opportunity with that expedition to sample again kind of the similar ice regime as we sampled in the southeastern Weddell Sea now just 1 year later. And this is just perfect because both ice regimes are basically then connected by that snow buoy. And this is what makes this data set so really unique for us. And you can see here then that we really, over the whole time period of the expedition, we had something like 17 or 18 ice stations. You can see it here on the right plot. They've been really all in that one small searching box for the Endurance. But even, well, it was kind of, so people really thought that I'm kind of stupid, that I'm sampling again and again and again the same ice regime, but it was really, really interesting for us because we could do actually similar work as we did on the Polarstern expedition in the southeastern Weddell Sea. So again, you can see it here in the panel on the to the right and in the bottom. We did again snow thickness and sea ice thickness measurements. We did again, as you see in the big picture, ice coring. So it was really basically the same work as we did before, which really allows us now to connect both data sets. And what becomes even more really, really cool is, so what you can see now here in the lower panel, you can see again the map and in black the trajectory of the buoy. And then we backtracked all sampled ice stations now from the Endurance expedition to the southeastern Weddell Sea. And you can see that really all ice stations that we sampled somehow came, of course, from the southeastern Weddell Sea, but they really also cover the whole area where we sampled the year before. So we can really say that we really sampled the same ice regimes twice. So once in 2021, once in 2022, and that's pretty cool. And in addition, you can see in the upper panel now the evolution of the snow accumulation. And I really want to highlight that that this is the snow accumulation and not the snow depth, and why I would just talk about in a minute. So what you can see from here is, so we started in the southeastern here on that side with a roughly 40 centimeters, and then it kind of increased a little, and then we had a slight decrease until March in this year because the buoy really reached kind of the ice edge there got a lot of solar radiation input, and so the snow melted a little. So when we just remember again what I said about the southeastern Weddell Sea, where we had a modal snow depth between 10 and 60 centimeters. We didn't have any superimposed ice, and we had a mean snow ice layer thickness of 18 centimeters. And we would now assume that when we look into the northwestern Weddell Sea area, so like 1 year later, that we would see something like 60, 70, 80 centimeters of snow. But what we actually saw are only 5 to 20 centimeters. And on average, it had been like 15 centimeters. And the reason are exactly the processes that I was mentioning before. So the formation of superimposed ice and the formation of snow ice. And we are just still right now inside of the analysis of the data source. The SCAR conference is like 2 weeks too early for us. So in 2 weeks, we have the whole data processing done. So far, I can only say that we had around 10 centimeters of superimposed ice, and the snow ice layer is still to be determined because we are still, as I mentioned, analyzing the isotope samples. But however, what I can really say is that this is a really nice example and data set really to show how the processes and properties change over the course of 1 year, how important those internal processes at the snow ice interface are, and that this data set now gives us a lot of opportunities for many different studies and thoughts in terms of internal processes. And those are here just now shown some potential questions that we want to answer. So as I said, so on the one hand, of course, in general, everything about the snow properties and processes at the snow ice interface, related to also different atmospheric conditions, because the snow buoy does not only measure the snow accumulation, but also the air temperature and air pressure, but also talking about the isotopic composition of the snow. How does it change along such a trajectory? Also, this is something really unique, that we have, again, the possibility to sample twice per year, twice the same ice regime, having also the atmospheric conditions in between. And with that, I'm done. I thank you for your attention, and I'm happy to answer any questions in the chat. Thank you.
Stephanie, there is a question for you in the chat box. Where do you find most snow ice? Near coast or ice edge?
Say again more. Say again the question. Where do I find what?
Where do you find most snow ice combination?
More snow ice. Well, I mean, it's not that related. It's not that related to whether it's more the coast or more like internally. It's really more about the latitude in general, because, well, for example, so you would have a lot of snow in the really southern Weddell Sea, but it's related to being close to the continent, yes. And of course, there also you have less solar radiation input, and therefore you have less melting, and therefore you have the potential of more snow ice formation because of the heavy snow load. So having that in mind, and when we then say that in general the sea ice edge is further to the south, then you would have always more snow ice in the southern part. However, this is then also again the question of how old is the ice. Is it like perennial ice or is it seasonal ice? So those are more the questions than the actual location.
Okay, thanks Stephanie for this wonderful talk on evolution of Weddell Sea ice drifting. Next, I invite Ms. Indrani Pujara. She'll be talking about identifying the drivers of anomalous sea ice drift in the Weddell Sea sector and the Indian Ocean sector of East Antarctica.
Hello everyone, am I audible?
Yes, you are audible. Just share your slide. share your presentation?
My screen is visible. No?
Yes, it is visible, and just make it full screen. Yes, absolutely right.
Good afternoon, everyone. I will be talking about the identifying the drivers of the anomalous sea ice retreat in the Weddell Sea sector and the Indian Ocean sector of East Antarctica. Antarctic sea ice affects the global climate, regional climate, and ecosystems. Because ice is more reflective than the liquid water, it plays a significant role in maintaining the Earth's energy balance and helping to keep the polar regions cool. Sea ice also keep the air cool by forming a barrier between the cold air above and the warmer air in water below. Antarctic ice is an important part of for the habitat like penguins, seals, and other animals like seabirds and Antarctic seals also. The Weddell Sea is a unique region containing the largest amount of the Antarctic multi-year sea ice. Importance of the Indian Ocean sector of Antarctica is known for the bottom water formation due to the enhanced sea ice production and the subsequent rainy rejection. Antarctica modulates the global climate through its influence on Asian and Indian summer monsoon, the location of the intertropical convergence zones, and the thermohaline circulation. Sea ice plays an important role in modulating the global climate system by influencing the atmosphere and the oceanic circulations. Variability and change in the Weddell sea ice cover is important for many atmospheric, oceanographic, biological, and chemical processes, as well as the logistic activities. Antarctic sea ice trend has been steady, but in the recent years, sea ice extent is going downwards. Recent decrease of sea ice in the Weddell Sea sector is also reported. So we have used sea ice concentration data from US NSIDC for the year 1979 to 2021. Sea ice area was computed as the total area of sea ice over the all pixels, and we examined the anomalies of the daily sea ice concentration and sea ice area of the Weddell Sea sector and the Indian Ocean sector. And 850 hectopascal geopotential and 10-meter wind data were collected from ERA interim. So first, we are looking into the variability of sea ice of Weddell Sea sector, and then we will move forward to the Indian Ocean sector of East Antarctica. Some of the recent years have shown anomalous reduction of sea ices. Following those, the daily anomaly of sea ice area is calculated and compared against the 2 sigma levels of daily sea ice area time series to identify the anomalous years and the seasons for both the sectors. Here, less than 2 sigma level for the Weddell Sea sector, 2 years are indicating like 1990 and 2016, and less than 1 sigma level, the corresponding years are 1983, 1986, 99, and 2018 and 21. Here we have taken the period around the austral spring for the year 1990 and 2017 to check the anomalous behavior of the sea ice in the Weddell Sea sector. And for the Indian Ocean sector, sea ice anomaly is showing less than 2 sigma level. It's the corresponding years are 1996 and 2016, and less than 1 sigma level, the year is 1986. Just like Weddell Sea sector, for the Indian Ocean sector, we have taken into account the period around the austral spring for the year 1996 and 2016. We choose to look around into all the anomalous years over the whole period for the anomalous sea ice retreat. Here we have considered years like 1983, 86, 90, 2016, 17, and 18, and with a duration of total 195 anomalous days. Now here the corresponding years, months, and the anomalous sea ice retreat days are given here. To understand the synoptic conditions driving those changes, the composite map of geopotential height anomalies at 850 hectopascal and 10-meter wind anomalies were computed. The following patterns we got. If we focus on August, that is of the Weddell Sea sector as well as the Indian Ocean sector for 2018, we are getting that a strong northerly flow, and in the Indian Ocean sector, a negative anomaly has been created and a sea ice reduction we are getting. And for 17 September and October, in Weddell Sea sector, we are getting some northerly flow, and a strong depression has been created. And in October 17 and end of October in Indian Ocean sector, we are getting two opposite kind of phenomena. A strong negative anomaly has been created, and just after that, a strong positive anomaly has been created, and also sea ice retreat we are getting. And same and similar kind of patterns we are getting for December 17 and November 17 also. Here November 16 and December 16 for the Weddell Sea sector and the Indian Ocean sector. Here northerly flow we are getting, but also the southerly flow we are getting in the Indian Ocean sector. Some other reasons are also there. In the year 1990, in both the sectors, a strong negative anomaly has been created and strong depression has been created in Weddell Sea sector as well as in the Indian Ocean sector. So as a result, we can say that the atmospheric circulation is the dominant driver, and the sea ice reduction is happening in both the sectors. So as a summary, I can say like anomalous retreat occurred in the Weddell Sea sector and the Indian Ocean sector in the years 1983, 86 and 90, and 2016, 17 and 18 during the austral spring. In the Weddell Sea sector, which has the greatest amount of multi-year sea ice, the sea ice retreat was associated with a deep depression that gave a strong northerly flow across the area. Sea ice variability results from the changes in the atmosphere and the oceanic conditions, although the former is thought to be the most significant since there is a high correlation in between the anomalies in the sea ice concentration and the near surface wind field. The atmospheric circulation at high southern latitude were clearly anomalous in those years, and there is a strong correlation in between the marked period at the north of the northerly atmospheric flow and the ice retreat. For the future work, I will do some statistical methods like PCA, self-urbanizing maps, and machine learning to identify the dominant patterns and recognize their drivers and how they are connected to the forcing. And the variability of Antarctic sea ice area can be related to several large atmospheric mechanisms, circular mechanism like SAM, zonal web 3, ENSO, PDO, etc. And we will in future investigate the importance of wind forcing and SST in the East Antarctica. Thank you for your attention.
Thanks, Indrani, for presenting your research work on the drivers of anomalous sea ice retreat. Now, in this next slot of the session, let me invite Dr. Lejang Yu for his presentation on the impact of the Indian Ocean Basin Mode on Antarctic sea ice concentration in interannual time scale. I would request CART IT team to play the video.
Hello everyone, my name is Lejang Yu. I come from Polar Research Institute of China. My topic is the impact of the Indian Ocean Basin Mode on Antarctic sea ice concentration in interannual time scale, at least of the author. My topic includes 4 parts: review data sets, results, and conclusion. There are a lot of influence factors of Antarctic sea ice, such as SAM, East Pacific El Niño, Central Pacific El Niño, Amazon Sea Low, Zone 1 3 mode, Indian Ocean Dipole. But later is known the Indian Ocean Basin Mode. Indian Ocean Basin Mode is the first mode. So the tropic Indian Ocean SIT, but the LBM is related to the Antarctic sea ice variability. This is the second mode.
Is there any problem of playing this video?
Hello. Hi, this is Manoj from Tech Team. Can you please tell us where the previous screen went so that we can play from there? 1, 2, 3, 4. Hello.
You can you start playing that video. You start playing the video.
Okay.
Yeah. Then maybe after around some 1 minute gap, you can maintain.
I mean, you can see my slide number, slide number 1, 2,
slide number,
3.
I think 5.
Okay, 5, right.
This is the second mode. Second mode is play more than 10% of the asset varies.
Same place it is
This
getting
is
stuck.
the dipole mode. The table shows the correlation between the LBM and the DMI. LDM and ENSO, LDM, DMI and ENSO. The DMI is the difference in the SS normalized between the west and the east tropical Indian Ocean. The correlation between LBM and Niño 3.4 is significant for the all season, but the significant correlation between LSM and the DMI occur in winter and spring. I remove the DMI signal. After remove the special pattern SAT normalized is more uniform. I examine the effect of the LBM on Antarctic sea ice concentration. Consider with the ENSO signal and without ENSO signal, I regress into the LBM index in autumn. Significantly positive sea ice cover occurs in Bermuda and Weather seas. Negative sea ice in the South Atlantic Ocean. Without a signal, the positive disappear, negative decrease. The special pattern of the mean sea level pressure shows the wave number 3. The anomalous southerly winds decrease the surface air temperature and push sea ice offshore, increase the sea ice cover. The anomalous northerly winds increase the surface air temperature and push sea ice inshore, decrease the sea ice cover. I regress other values onto the LBM index. This is less convective activity over the southwestern Pacific Ocean, corresponding negative Rossby wave source (RWS), and divergent alpha divergent wind produce the wave tree propagate into the Amazon and Bermuda and Weather Sea. The wave tree influence the mean sea level pressure normalized in the South Ocean. The green line is the wave tree. Similarly, I examine the screen time Antarctic sea ice concentration. This is significant positive sea ice cover in the Bering and Weddell Sea. The special pattern of the mean sea level pressure shows a negative phase of the SAM index. Cold air temperature produces more sea ice cover. The less convective activity over the southwestern Pacific Ocean generates a wave into the South Ocean. Another wave tree is excited over the southwestern Indian Ocean. Without answer signal, similarly, there are two wave trees, but the difference is the first wave tree is produced on the over the central Pacific Ocean. In summer, this is the depth structure of the anomalous sea ice concentration in Ross Sea. In winter, significant positive sea ice cover in the northeast Weddell Sea. The anomalous surface wind and air temperature can explain the anomalous sea ice cover. This anomalous mean sea level pressure result the wave trend. This is wave trend from tropical Pacific Ocean. Conclusion: this is a Taylor connection between the Indian Ocean basin mode and Antarctic sea ice anomalous, which is much stronger in spring, autumn than summer and winter. In particular, under the Pacific, under the positive phase of the LBM, significant positive sea ice occur in the Bering and North Weddell Sea. Negative in the Amazon Sea, the South Atlantic Ocean, and the coastal sea. This is teleconnected connection is established by the planetary wave tree excited over the tropical Indian Ocean and tropical Pacific Ocean, but is modulated by the El Niño. The LBM related Antarctic sea ice anomalous is largely consistent with the anomalous surface air temperature and wind fields associated with the LBM. My study is published in JRL. This is the JRL. Thank you.
Thanks, Lejing, for your talk on the impact of the Indian Ocean Basin Mode and the Antarctic sea ice concentration. And next, let me invite Dr. Arnab Mukherjee to start his presentation on role of snowfall forcing on sea ice variability in the Antarctic.
Yeah. Hello, I am audible.
Yes, you are audible.
Okay.
And
Today,
make it full screen mode. Make it full screen mode.
Make it full screen, right?
Is it full screen?
Yeah, no, it's not full screen. I'll make it.
Yeah, just make it.
Okay. So today, myself, Dr. Anil Mukherjee. So I am working in NCPR as a scientist. So today, my presentation topic is role of snowfall forcing on sea ice variability in the Arctic. So, what I am using a global ocean sea ice model which is developed at NCPR, known as the modular ocean model with sea ice simulator MOMSIS, and that model has a global domain with 25-kilometer resolution in longitude and latitude direction. And we have used that tripolar grid on polar regions, the 3 poles, Arctic, and mostly the 2, removing the singularity in the Arctic and ocean. And we start the model after 100 years of spin up using era 5 forcing based on atmospheric parameters, all the like not net wave, short wave, long wave radiation. So that model will start. So that is the domain of the model. We say is based on the, it is a global model and it covers from entire globe and both the Arctic and Antarctic. So main objective of the first is to show some validation of the model in order to simulate that sea ice, observed sea ice concentration and sea surface temperature in the Antarctic region. So Antarctic region we choose from around start from 50 to 90, but in the north, south section, and for entire globe. And we have tried to correlate with ABHR observed sea surface temperature and sea surface concentration. Sea ice is the sea ice concentration and the sea surface temperature. So what we found is that the correlation is slightly better for sea surface temperature is higher, but it's not bad for sea ice concentration, but also good. And also we found the root mean percentage error, and that we found that there are except few locations we found overall the very good match with less RMSE error between models and ABHR. So after that we used to try our objective was there to show the decadal change. So we ordered to find the decadal change between, we have choose the recent 2 decades between 2010 and 2019 and 2000 to 2009. And we have divided into the 4 seasons, that is the summer, autumn, and winter and spring. And that 4 season, we first check that left-hand side, which actually shows that ABHR, the satellite data, what is the sea ice concentration, actually it's showing that whatever changes in the recent decade. So in order to find the decadal change, we first use the climatology between 2010 to 2019, and then we found the 2000 to 2009. So that last 20 years of this one, and we subtract the 2010 to 2009 climatology with 2000 to 2000, so that whatever if changes is high, that means sea ice is increased in the recent decade compared to previous decade. So if you found that divided into the 2 regions like Eastern Antarctic and Western Antarctic, what actually observation shows that during the summer, it's mostly the eastern, there is a slightly increases there, but in the Northern Sea region, you can clearly see there is a sea ice has decreased, but it's not uniform like we used to see in the Arctic. So in the recent decade, in the during winter and spring, except a few occasions or few mostly in that lower latitude, actually there is a decrease of sea ice, but higher latitude there are some increase also there, even though it is small. So during all the seasons. So what model actually capture, model also capture, but except there are some mostly Eastern Antarctic, it has some tendencies that it mostly shows the sea ice decreases, but that is clearly shows that like Order Sea, it has decreases well. And that is the point that in that Eastern Indian Ocean sector, there is slight increases that we found, but it is sometimes it decreases, sometimes small. So overall, it's actually not bad, but it's okay. And then we found that SST, which we found that model is slightly better in simulating the decadal change. So if we see the same thing, decadal change for the SST, we found is that SST had increased in the Eastern Antarctic region compared to Western, and that clearly shows both in the model and observation. So that is one of the reasons that model is better predictable on sea ice sea surface temperature very well. And sea ice data also has a limitation. But the Eastern Antarctic, what is warming actually, that clearly found using the model which is configured here in the global model intensive pure. So now the objective of the the presentation was there to related to the snowfall forcing on how the contribute actually snowfall forcing. So what actually it has been found that snowfall is contributed not much actually into this model because it's snowfall used as a for model forcing. So what actually we did a one numerical experiment by remove the snowfall forcing from the model, and we given the name as MOMSIS no snow. Then we subtract the MOM model, that MOMSIS model with MOM no snow, so which represent the impact of snowfall. So what actually shows that the snowfall mostly responsible for, there is a if the snowfall is responsible, it should be it produce the more snow. More sea ice concentration at that is expected actually. So what we found that it is not uniform all over the Eastern Antarctic domain. So in the Eastern Antarctic during the summer there is an increase and there is a decrease also. In the adult sea there is actually decrease. So is it related to that there is a decadal change in the snow forcing or not? To find out that we whatever we have used the snow forcing from era 5. So that is era 5 analysis is our model parameter. So what actually found that in the recent decade snowfall is not continuously decreases or increases. In some location it has increased, or some like in the Indian Ocean part you can see it also varies, but during winter time you can see that adult sea region there is a strong decrease of snowfall rate for some locations. So actually it is a varying actually from spatial variability during, but mostly we are seeing during winter, and it is expected the winter snowfall is more. So that's, but we have also similarly the sea ice, not much difference, but even there is some location where we have observed that snowfall actually plays a role in decadal change of SST also as well, like in like that is a Eastern, that is the West Sea, there is a slightly increase of SST you have observed because snowfall has actually some location it has decreased. So actually it should be opposite, like SIC, whenever there is a decrease of SIC decadal due to snowfall, and it should increase the SST as well as and that is the expected. So some results, so what actually seeing is that even though its contribution is not much, like the scale is 0.5 to 0.5 to 5%, and SST also 0.1 to that one, but that is a more need to be done. But it shows that there is a way that we can show that snowfall is important for decadal change of SIC and SST. So in summary, what are the conclusion we have observed is that MOMSIS developed a tendency with a higher correlation for SST compared to SIC. Obviously, so SST decadal change much better, and both models actually shows that decadal warming Eastern Antarctic region, and that clearly shows the model, and that is a positive decadal change of snowfall whatever is observed for SST as well as that snowfall increases. So it contribution around 5 to 10%, and that the model actually implies that snowfall play a significant role for the decadal weakening of SIC in the Antarctic and decadal increase of SST in the region, and both vice versa also. So thank you. If any question, yeah.
Thanks, Arnab. I think there is one question in the chat box. Have you considered sea ice thickness, volume?
Yeah, I considered, but we have not showed here. So we have also observed that sea ice thickness is also very prominent in terms of snowfall. So its figure was not attached here. Yeah.
Okay, there is one more question. Why there is a different sign of snow impact?
Different sign of snow impact, which figure actually? Can you elaborate? Snow impact different sign mean it's a either actually it should be like anomaly, it should be change, like it should be positive or negative. So snow is increases, sea ice also has to increases, it's like that. But different sign means I don't understand that. Yeah. Anyway.
Okay.
I think we can talk later on that one.
Yeah, you can respond to it. Yeah, you can respond to it. So
yeah.
Later on you can.
So actually, was which figure you want to clarify? Then it should be better.
That's what you can just make a query. And just you respond to it. It is already there in the chat box.
Okay.
Just answer it. Okay. So.
Yeah, I will do that one.
Oh yeah. Yes. Later on you can do that.
Yeah.
So now may I please invite the next speaker, Ms. Shreya Trivedi. She'll be talking about an assessment of Antarctic sea ice thickness in CMIP6 simulations with the comparison to the observations. Shreya, can you start your presentation? Anab, you can mute your audio and video.
Yeah.
Shreya is available. IT team, can you check whether Shreya is available or not?
She's not there at the moment. She's not there.
Okay, she's not there.
Yeah, she's there. She's
there.
IT team, I think she's present actually. So yeah.
So can you invite otherwise?
Yes, she's there.
Yeah, I'm here. Thank you very much. And I'm extremely sorry. There was some problem from my end.
Okay, we are waiting. Not a issue. We have enough.
Okay. Yeah, I'm sorry. Yeah, I think now I can do that.
Yes.
I'll just start sharing my screen.
Yeah, you start sharing your screen.
Is it visible now?
Yes, it is visible, and please just make it full screen. Yeah, absolutely.
Okay, yeah, I'm going to do that.
It is fine. Yeah, perfect.
Okay, thank you very much. So hello everyone. In this presentation, I'm going to talk about the observed sea ice thickness and how CMIP6 has simulated the sea ice thickness observations. So to begin with, I will first address why at all I have selected this study, which brings me to the importance of the study. So first of all, sea ice thickness tends to be the least studied sea ice parameter in the Southern Ocean. And it's mainly because of its least availability and accessibility. And the data set which is available is of very short time period. And also it comes with large errors and noise. And that is why it becomes very important for us to understand sea ice thickness as a parameter and how well the models have simulated it. This brings me to the objective of the study. And that what exactly am I going to do in this study? So you can see my study area. These are the 4 regions. And when I'm going to talk about these sectors or the regions, this is what this is the boundary where what I will be basically talking about. So in my study, I will be trying to answer, or I have answered 2 questions and the first one being that how well are CMIP6 sea ice models simulating the observed sea ice thickness? And the second will be that which model or models are showing maximum agreement with the observed sea ice thickness over the different regions. A little bit about the observation data set. This has been adopted from ESA CCI Plus from 2 radar altimeter missions, which is ENVISAT and CryoSat-2. It's a monthly gridded sea ice thickness data, and it's a full cycle data, starts from May 2002 to 2017. It's a very small time period, as I mentioned, that this is a shortcoming of the available sea ice thickness observed data sets. However, to match it with the CMIP6 historical time period, I have cut it short further. And now the observation period is only from May 2002 to December 2014. This is the data source, a paper by Hendrick et al. 2018, and he talks in detail about how sea ice thickness has been processed. I'm not going to go in detail. I'm just going to talk about what are the major 2 steps which have been taken. First, the freeboard height has been estimated, and then this freeboard height was converted into sea ice thickness. And that's the data I'm using in this study. About the CMIP6 model data, first of all, I started out with 43 models, 43 CMIP6 models. I had to cut it short by 7 models. And in this, I'm using the 35 models, as you can see over here. The rationale for getting away with the 7 models was because they were showing very high biases and there was a lot of skewness in my results. The another thing is that only R1 ensembles have been used for every model. A little bit about my methodology. I'll be looking into the climatological characteristics, how the seasonal cycle of SIT looks like in different regions, temporal and spatial variabilities by comparing the annual and seasonal anomalies, looking at the spatial and temporal trends. And finally, the selection of the models have been done based on the correlations and the mean absolute errors or the biases in the model. Climatological and the annual cycles, these are basically the results I've started with. It's a very preliminary study. In this, I'm mainly looking at what the results, what the data set looks like, both the observed and the models. So the questions of why and how is something I have not addressed as yet, and that's something which I'm going to do in future. So as of now, what you see here in the climatological cycle, the reds are basically the observed means, and the blues are the multimodal means. And what is filled in between, the light blue, is the interquartile range. So the striking feature we look at the observed cycle is that the thinnest month for all the regions is February and March, depending on what region it is. And the thickest month tends to be August and September. And but when we look at the models, there is a delay in the thinning as well as the thickening of the sea ice. So if we look at the thinning of the sea ice, we see that there is a delay of about 3 months in the Weddell Sea, about 2 months in the Amundsen-Bellingshausen and the Ross Sea. And it's only the East Antarctic where the minimum month coincides with the observation of that of the model. Same is happening with the thickest month. There is a delay which has been seen in almost every sector. Then looking at the linear trends in sea ice thickness, again, what you see here, the reds are the observed trends and the blues are the trends in the multimodal mean. The black dots here are the individual trends for every 35 models. So clearly there seems to be a pattern in the increase and decrease of sea ice thickness across all the months and the seasons. So the first column here is for the months and the second column here is for the seasons. So just looking at it, we can see that Weddell Sea tends to be the sector which has the thickest sea ice with the strongest positive sea ice trends, while Amundsen-Bellingshausen follows it. And Ross Sea and East Antarctic have the strongest negative trends with thinnest sea ice in all the sectors. But when we look at the multimodal mean, as expected, all of them are showing a negative trend in sea ice thickness. And that's something which is expected out of models because models are projecting high temperatures. So we will be expecting lower sea ice parameters. A striking feature again is one here in the Ross Sea. In the February month, there is a slight positive trend, that is an increase in the sea ice thickness, and similar is seen in the DJF or the summer season of Antarctica as well. There is a slight increase, and it's interesting because February happens to be the month where the leanest sea ice is observed. So that's something which is interesting, and I'm going to look into it in future, that what are the reasons for that. Moving on to the statistical analysis. So this is basically for the selection of the models, and I have used correlations and the mean absolute deviations or the biases from the observation. What you see here is for the Amundsen-Bellingshausen sector, and a similar analysis has been done for all the 4 sectors. And on the basis of positive correlations and the least errors, I have selected 5 models, and they were performing really well for all the 4 sectors which I have mentioned. So besides that, there is something else I'm going to talk about very quickly, that if we look at the overall performance of CMIP6 models in this sector, right here, which is the March, April, May, or the spring sector, models are performing consistently well, relatively well, I should say, compared to the other seasons and also annually, because the errors are quite low. Another thing is I would want to specially mention about models of ACCESS and CESM2. These are the 2 models which have performed very well in simulating the sea ice extents and concentrations. But when we look at the sea ice thickness performance, they were giving a negative correlation. And also, I looked a little bit of how their climatological cycles are looking, and these cycles were also falling out of sync. The black one is the observed, and these are the CESM and access models. In fact, the thinnest month happens to be one of the thickest months in these models. So there was something wrong with it, or maybe something which I am not able to see. So that's something else I'm going to look into future. Finally, the list of the 5 models which I have selected for simulating SITS, CNRM, CAN ESM, MPI, MCM, and NOR CPM1. A little bit more about how the models are looking in their climatological cycle. So in the black, we see the observation, and overall, all these models, the ones which I have selected, they have a very similar annual cycle when compared to observation. Another striking feature was about this particular model of MCM. At present, you won't be able to see MCM. It's in red and it is completely flowed, and which means that it has very high underestimation, very low average values. And the average values it showed were about 28 times smaller than that what were observed. But when I changed the scale, and I looked closely, the annual cycle of MCM was very closely corresponding to the observation. The peaks were matching, the troughs were matching. So it was very interesting to see that how this model with very high underestimation was giving a great climatological cycle. Finally, looking at the spatial trends, what you see here is observed spatial trends, the ones with MCM, and the selected model ensembles. Selected model ensembles is nothing but an average of all the 5 selected models. And overall, as expected, again, there is a primarily declining trend in sea ice thickness. You see all red over here, except for a little patch on the side of the peninsula where there is a slight positive trend which can be noticed. While observation, we see that Weddell sector was showing an increase in the sea ice thickness, while Ross was showing a declining or a negative sea ice thickness trend. And MCM out of all the models was the only model which was replicating it well. And the patterns were quite similar to that of the observation. So that's something else which I would want to see that what's exactly happening in MCM. Then when I looked at different seasons, again, I had the same result that MCM was doing a great simulation. However, we have to keep in mind that MCM, as I mentioned, was showing very high underestimation at the same time too. Coming to the conclusions, so as expected, there was a negative or a declining trend in sea ice thickness for all the CMIP6 models. Then they were also showing a delay in the minimum and the maximum sea ice thickness month by 1 to 3 months, depending on the regions. And also, again, as expected, CMIP6 models were showing very large discrepancies and very high intermodal spread as well. So for now, MCM might look as a model which overall shows a very great resemblance to observation. But in future, what I'm planning to do is that I will be breaking it down for every region, and I'm going to select a model which corresponds maximum to that particular region. In the end, thank you very much. I would want to extend my gratitude to my advisor and my colleague who helped me with this presentation, and for you all being a wonderful audience. Thank you very much.
Thanks, Shreya, for a wonderful talk and very important efforts undertaken for analyzing the sea ice thickness. And I think just let me find out if at all any questions are there. There is no question. Okay, there is one question. How are the special sea ice thickness distribution in models? How are the special sea ice thickness distribution in the models?
So as I addressed initially, that I started out with 43 models and I chose 35 models, and I had to do away with 7 models. The 7 models were showing very, very high anomalies, and overall all the models were showing a declining trend. The averages were quite low for some models. There were averages which were very, very high in the other models. So I had to actually select the models which were very close to the observation. So the models were having very high intermodal spread. It was not very great. And I would not expect models to show great sea ice thickness because the observation itself are not very great. So I don't know if I answered your question correctly, but they were showing very mixed responses, and they were not very good. That's all I could say.
Thanks, Shreya. And the next speaker is Mr. Thomas Chungkam. The title of his presentation is Antarctic sea ice concentration estimation using bifrequency Sorrel Altica data. I request SCAR IT team to play the pre-recorded video.
A very good afternoon, everyone. My name is Jungkam Thompson. Today I will be presenting our study on the topic Antarctic sea ice concentration estimation using bi-frequency Southern Altica data. The authors for this study are Jungkam Thompson, myself, and Dr. Kamaljit Singh from Manipur Technical University, and Dr. Sanjeev Oza, Dr. Purvi Joshi, Dr. Sushil Singh, and Dr. Ismohan from Space Application Center, Indian Space Research Organization. So for our outline, we have the introduction to the sea ice concentration or study area and data, the methodology of behind the estimation of the sea ice concentration, the results and discussion, and finally we have the conclusion. So sea ice concentration is defined as the ratio of the ice covered area to the total area for a given sea ice region. It's an important indicator of climate change. It is one of the most critical polar ocean measurements provided by passive microwave data, and it is also required in the estimation of the total volume of sea ice area, sea ice extent, and sea ice thickness. So our study area is in Antarctic. Here we have the brightness temperature of Southern Altica, dBK at 37 GHz and dBK at 23.8 GHz. So we use a primary data, level 2 Southern Altica geophysical data records at brightness temperature dBK of 23.8 GHz and dBK at 37 GHz at a polar stereographic projection south at a grid resolution of 23 by 37 kilometers. Our study period consists of all the months of the year 2020. And here we have the secondary data for comparison. We use the National Snow and Ice Data Center Climate Data Record, NSIDC CDR SIC product, which is also projected at the same subtle resolution of 28 by 37 kilometer with the same study period. The reason why we choose this NSIDC CDR product is that it is a good, consistent, and well-established product. In the methodology section, we have the scatter plot of dBK versus dBK. And on the right, we have the corresponding map of the scatter plot. So the purple region indicates open water region, that is the open water region on the Antarctic map. And the red region indicates the new ice. And also there is also another ice region which is colored by magenta. And here we had, and these magenta regions are mainly represents all or multi-year ice. So here we have the schematic diagram of scatter plot of dBK versus dBK. And here we have the time points. The time points are the typical brightness temperature values at 100% sea ice concentration and 0% sea ice concentration. So the time point A is calculated by taking the mean of dBK and K plus twice the standard deviation, and the time point D as the mean minus twice standard deviation, and the time point O as the mean minus twice standard deviation. Lines UV and SD are drawn perpendicular to OAA, and for a point on or above DA, that is the point Z, the SIC is given 100%, and for a point E above the line SD, the SIC is given 100%, and for a point F below the line UV, the SIC is given 0%. For a point Y between the line DA and OA, the line OY is extended to intersect the ice line DA at G, and the SIC is calculated by taking the ratio OY divided by OG and then multiplied by 100 to give the SIC in percentage. And for the point P on the line OA, the SIC is calculated by taking the ratio of OP to OA and then multiplied by 100. And for a point X on the right of OA, the SIC is given by the ratio of OX by OA and then multiplied by 100. So the above algorithm is implemented in Python, and the subtle SIC product for a winter month and for a summer month is shown here. Here we also made a qualitative analysis between our subtle SIC product and NSIDC CDR, and we also made a median filter kernel with kernel size 3 and kernel size 5. The reason why we apply median filter is that for a particular pixel and the surrounding pixels, the same weather and atmospheric condition is governed. Here also we made the same comparison between our thorough data and NSIDC CDR SIC product for a summer month, February 2020, and the comparison shows that our thorough data with the median filter 3 and 5 appears to be similar with the NSIDC CDR SIC product. And so we also made a quantitative analysis by calculating the root mean square error for all the months of the year 2020 with kernel size 3 and 5. As we can see that the RMSE values for the summer months are much higher than the winter months. This is because of the variability of the brightness temperature due to wet snow and melt bonding effects. So in conclusion, we have estimated the SICs from the subtle brightness temperatures and compared them with the NSIDC CDR data. Calculation of RMSE values shows satisfactory results. We also get the CIC extent as a byproduct. Subtle SIC at 25 km grid resolution will be our next study. And in conclusion, our subtle SIC products can be used as a basic dataset for SIC records. So on behalf of the other authors and myself, I would like to thank the organizing committee for giving us the opportunity to present our study. Thank you.
Thanks, Thompson, for your recorded presentation on utilization of Sorrel Altica for estimating CIS concentration. Next, I'd like to invite Professor Erin Mont, who will be talking about summer CIS variability on the Antarctic margin during the last glacial period reconstructed from snow petrel stomach oil deposits. So, Erin, I think she's there. So, please start your presentation.
Thank you. Can you see my slides okay?
Your slides are visible, so please go to the presentation. Yeah.
Thank you. I'd like to thank the organizers for a really fascinating session about sea ice. I'm going to take you to a slightly different time window and also a different way of thinking about sea ice, which is to use these beautiful Antarctic seabirds, the snow petrels, which are very closely associated with the sea ice. And so in this talk, I'd just like to show you some new ways that we're using the snow petrels themselves as indicators of past sea ice. So why should we be concerned about longer term perspectives on sea ice, so geological records of sea ice? Well, the first reason is that we can use these archives to set our recent trends in sea ice into a longer term context. So trying to think about whether changes we see in the instrumental record, which we've heard about in this session, are part of longer term cycles or longer term trends. We can also then use these records to explore the forcings and feedbacks on the sea ice by looking at climate changes which are different to the recent. And that also then leads into an ability to use these climate windows of the past as tests for climate models. So by looking at long-term changes over decades and millennia, we can really look at quite different climate conditions and think about how that influenced sea ice. So an example here on this map, it shows you some data points from the last 2,000 years. These are the archives we normally use. So ice core data and also marine sediments, which we can use to extend our instrumental record back in time. We've also been able to push that data back over much larger time climate cycles. So this data shows you the last 130,000 years. And over that time window, we've seen the Antarctic ice sheet and Antarctic sea ice extent being much, much larger than present around 25 to 30,000 years ago. And then even further back, we get to what's called the last interglacial, when temperatures were warmer than present. And so it's interesting to understand how the sea ice has responded to that. But you may notice on these maps that there's relatively little data from within the sea ice pack itself. So a lot of our evidence has been really focusing on sea ice extent and identifying the sea ice margins. And so what I'd like to show you today is a new way that we're approaching getting information about the sea ice environment. So we want to use the snow petrels as a new biological archive. So I just want to lead you through how this system is working. So step one is that today we know that snow petrels forage in close association with the sea ice. So they're very closely associated with our sea ice environment. And there they're feeding on a mixture of fish and krill and squid in varying quantities, depending on the access to the environment, but also potentially sea ice conditions. But during the spring and summer, they're nesting on land, they're nesting on the mountains within the Antarctic ice sheet. And here they convert that prey into a stomach oil to feed their chicks and also to fend off predators. And at those nesting sites, what we find is an accumulation of stomach oils over time. So hopefully you can see here the snow petrel sitting surrounded by an accumulation of this waxy deposit. If we cut open those deposits, what we find are these beautiful layered sequences going from old material at the base to younger material at the top. And effectively, this is a record of stomach oil being spat out onto the environment over thousands of years. So what we're trying to do in this work is to reconstruct snow petrel diet using these deposits and use that to explore sea ice changes of the past. Our area of focus is borders the Weddell Sea region and the Indian sector of the Southern Ocean. So we have a series of archives from different nunataks and different mountain ranges. And hopefully you can see here the shaded colors which correspond to each of our sampling sites. What the shading shows you is how far the snow petrels will forage away from the nest when they are either incubating their egg or looking after their chick. And hopefully you can see that what this is going to provide us is an integrated signal of the sea ice environment closer to shore than those marine sediment records I showed earlier. In today's presentation, I just want to zoom in on one of our areas of study, which is in this region of Dronning Maudland called the Untersee Oasis, where we've been exploring the stomach oil chemistry as evidence for reconstructing snow petrel diet through time. So here's the same deposit that I showed earlier, now with its dates constraining our time window, and we can see that it spans from around 22,500 years before present back to about 28,500 years before present. The significance of this time window is that we know from the marine sediment cores that Antarctic sea ice extent reached its maximum during this time between about 22 and 30,000 years ago. And at this time, the sea ice edge was several thousand kilometers away from the continent. The first thing that we've done with the deposits is we've scanned them. This is what's called XRF scanning. So we look at the elemental composition of the deposit and look at key elements which might tell us about snow petrel diet. So I want to draw your attention to the central diagram here in orange, which shows us the relative abundance of copper in the record, which we are interpreting as evidence for Antarctic krill being part of the diet. As we look down this deposit, we see there's an area at the top with relatively high copper, a window where copper drops to very low concentrations, and an increase in copper towards the base of the deposit. So the way that we've interpreted this data is that the snow petrel diet has been fluctuating. In the upper part of this deposit, we have a mixed diet of krill and squid, because we can see the evidence for krill here. In the center, we lose some of that krill contribution, and at the base of the deposit, we return to a mixed diet, which is more like we see today. This interval of low krill in the center is prolonged. So it's around 1,000 years of time when the snow petrels were foraging on much less krill within their diets. This is an extensive period where the diet has changed. We also have been looking at fatty acids and other biochemicals in our deposits. This shows you here records in grey of the relative abundance of fatty acids, which might also tell us the relative importance of krill versus fish within the snow petrel diet. And again, here we see this window here where we have relatively low abundance of krill corresponding to this low abundance of copper. So this the axis here has been switched so that this is low copper and this is high. So we also then see this shift between low krill and a mixed diet. In the green here and in the purple, we see markers for enhanced phytoplankton contributions, which we think are representative of actually more fish being present in the diet, and that a shorter food chain is allowing preservation of some of these indicators. But in terms of our sea ice environment, what we're interested in doing next is trying to understand what this change in diet might tell us also about the sea ice itself. How is the sea ice environment changing through time? And one of the tools we can use is to look at the stable isotope variations. These are used today as ways of tracking foraging habitat in seabirds and in other components of the ecosystem. And in red here, we have the carbon isotope composition of the fatty acid, which comes from krill. And we can see that there are long-term shifts in this indicator, and then some more variability in the upper horizon. If we combine all of this data and we use modern snow petrel behavior as a guide, what we think is happening is that the snow petrels are foraging for their food in different parts of our environment. So that in this central window where the krill disappear, this is suggesting that they're foraging very close to shore in an environment where krill are not abundant and fish are more important for the diet. And then before and after that window, they're foraging in deeper waters offshore, where we see that mixed signal of krill and fish today. So one interpretation of this indicator is that during this time window, the sea ice margin may have been fluctuating from being located further offshore to being quite closely related to the continental shelf, remembering that this is a spring or summer sea ice margin reconstruction, because this is when the snow petrels are foraging. The issue that we have with this recording of fluctuating sea ice margin is that, as I mentioned, this time window is when Antarctic sea ice extent was at its maximum. And the margin would have been far beyond the snow petrel foraging range. So instead, well, as we see here, so this is our deposit, and this is where the sea ice edge was located. This shaded zone shows where we think the snow petrels can forage. So they can't have been feeding on a fluctuating sea ice margin. So we interpret instead that actually they were likely feeding in polynyas, which were located within a much larger sea ice pack than today during spring and summer. So a very different circumstance to today. And that perhaps this ocean and shelf environment switching relates to the availability of these coastal polynyas giving a shelf signal compared to more open ocean signals further offshore. The reason that this is important is that on long time scales over thousands of years, we think that Antarctic sea ice extent is really important for how CO2 and heat is exchanged between the ocean and the atmosphere, and might also be affecting Antarctic bottom water formation. So now we need to think about how to incorporate polynyas more appropriately in some of those models which allow us to quantify the nature of those feedbacks. So just in conclusion, I wanted to show you a new way that we have of thinking about past sea ice environments using snow petrel stomach hole deposits. And our work is bringing this work from the glacial period right up to the present day to draw together information with the instrumental period. By linking diet to our modern feeding habits, we think we've identified use of polynyas during a much more extensive summer sea ice pack during the last glacial period, and that now we need to start thinking about what that means for climate feedbacks, but also climate forcing of sea ice during climate conditions which were very different to today, but which have evolved towards the system we have right now. And with that, I'll finish and thank you.
There is no question in the chat box. So thank you so much, Erin, for your very exciting work on sea ice reconstructions from snow petrel stomach oil deposits. And next, the speaker is Ms. Steffi Livera. The title of her presentation is Ocean Sea Ice Processes and their role in multi-month predictability of Antarctic sea ice. I think, okay, you are there in person. Okay, you can go ahead with the presentation.
Hi, everyone. I'm Steffi Libera. I'm a PhD student at the University of Tasmania, Australia, studying Antarctic sea ice and ocean interaction. In this talk, I will be giving the ice-ocean interaction perspective of Antarctic sea ice predictability. Antarctic sea ice is a critical component of the climate system. It provides a vital habitat for the Southern Ocean ecosystem, and it is important for us to understand the drivers of its variability and trends and to be able to predict it. In my study, we investigate the predictability of Antarctic sea ice and the physical processes that occur in the ocean that underlies this predictability. And in this talk, I will be touching on three main points. One is I explain what the predictability is, and then I go through the physical processes in the ocean that is underlying the sea ice predictability, and then finally go through the regional variability of Antarctic sea ice predictability. So what is predictability? In my study, I calculate the correlations in the forward-looking perspective. That is to say, we're looking for any anomalies that is persisting in that system or retained in that system, or to look at how a given initial state relates to the future state. And I'll try to explain that using this example of sea ice predictability from the Weddell Sea region. And this is the sea ice predictability from the initial month of January. And by saying that, I mean, I calculate the correlations from the total sea ice area in January against the total sea ice area in the future months. And here, from this high value of correlation and the hashings indicating that they are statistically significant, we can say that there is some anomaly or some signal in the system that is retained through the first few future months before it's being lost. Or this is an example of persistence of predictability. From the same region, I take another example, and this is the example from the initial month of October. And so again, the sea ice area is being correlated against the sea ice area in the future months. And in this case, you start to see that the high correlations after 2 initial months are lost, or there is a loss of predictability in the intermediate season before it recovers. And this is an example of re-emergence of predictability. So I used the sea ice predictability results from 2 initial months to explain persistence and re-emergence. But when I look at the sea ice predictability of a region, I calculate it for all initial months, and I get a result like this, and a result in the format of a matrix. And so here on the y-axis, I have all of the initial months, that is from January to December. And along the x-axis, I have the future months to which I've calculated the correlations. And I've shifted them so that the future months match along the x-axis. So when we have the results in such a format, we start to see that there is seasonality. So I've used this example along this first row for the January initial months to show the persistence, and then along the October one for the re-emergence. Now, when we look at the seasonal brackets, you start to see that along the summer months, there is a strong tendency to form persistence that we call a summer persistence. And then when it comes towards the spring season, there is a strong pattern of re-emergence, which we call as the spring re-emergence. And throughout our analysis, these 2 patterns are the main seasonal predictability patterns that we find. Now I will move to the oceanic processes underlying sea ice predictability. So previous studies have clearly established that ocean holds the memory that relates to the sea ice predictability, or that the upper ocean heat content is that what provides the memory for sea ice predictability. So we've already calculated, or I've already explained the sea ice predictability calculation. Now, from the model outputs, what we tried to find was to see if there was a signature in the ocean that would clearly help us explain the sea ice predictability. So for that, we calculated the oceanic predictability. So in the sea ice predictability, it was total sea ice area in the initial month being correlated against the sea ice area in the future months. For the oceanic predictability, we calculate the total sea ice area in the initial month against the upper ocean temperature in the future months. So here, for the bottom panel, you have the depth from 0 to about 200 meters, and then the correlations into the future months. And for the ocean, to follow the seasonal evolution of its structure, we use these contours. So this thick black line is the vertical temperature gradient maximum, which we use as the proxy for permanent pycnocline. And the dashed black line is the vertical density gradient maximum, which we use as a proxy for seasonal pycnocline so that we can follow the seasonal evolution of the upper ocean. Now let's look at the two results again. So the same examples that I've used from the January initial month, which represents now the summer persistence, and then from the October initial month, which represents the spring reemergence. So here you can see on the top panel for the sea ice predictability, you have strong positive correlations or strong correlations. Whereas when you look at the oceanic predictability, corresponding to those strong positive ones, you have strong negative correlations. That is to say, the sign is reversed or flipped. So for the ocean, it has to cool and lose or decrease temperature for the sea ice to form, as well as to sustain sea ice. So that inversion in temperature can be connected in that way. And here I'm going to use this example of predictability reemergence using this loss of predictability, which we call as predictability suppression. So this example here is quite consistent with the existing literature that explains the reemergence, the mechanism of reemergence. So during the summer months, the summer season, when the sea ice melts and produces the meltwater, the fresh water, and the strong stratification, the predictability in the ocean that was existing is isolated at the surface that causes this temporary loss in predictability. But when the sea ice forms again as the surface ocean cools and the mid-sea layer deepens and erodes the stratification, it allows the memory from the previous season to reemerge, producing the reemergence of predictability. And in these two panels, you can see that there is a loss of predictability in midwinter. And in this case, it's in July, future month. And that corresponds to the time when the seasonal pycnocline merges with the permanent pycnocline. And this we call as the predictability barrier. And if I continue on from the case where we have reemergence as the sea ice memory from the previous season entrains back into the mid-sea layer as the mid-sea layer deepens through the winter water layer. But once the mid-sea layer deepens further and reaches a point near the permanent pycnocline and reaches where it starts to interact with the deep ocean interior, which has no sea ice related memory, and entrains that water back into the mid-sea layer, it starts to change the ice ocean system conditions or the memory in that system, and therefore produces the loss of the memory. So that's the predictability barrier. And this is again explaining the same theory. So we're going to skip to this slide where I bring about or I talk about the ice ocean interaction perspective of sea ice predictability. So I've been explaining the results based on the oceanic predictability, and I said that I calculate the correlations between the total sea ice area in the initial month and the temperature in the upper ocean in the future months, which is to say these strong correlations that we find here, or the signature in the ocean that we find here, is in fact residual thermal signatures in the upper ocean that is related to sea ice processes that lingers in the ice ocean system and influences sea ice from one season to the other or between seasons or interannual timescales. And that itself is a signature of ice-ocean interaction. And this signature is just not static. It is very much dependent on the vertical ocean structure in that specific region. And that vertical ocean structure is evolving, and so is the signature. So this is clear signature of ice-ocean interaction. Now that I'll wrap the oceanic processes and move to the regional variability. Okay. So before I show all the results, I wanted to just remind that the summer persistent as marked in this box and the spring reemergence is the two main modes of seasonal predictability patterns that we observe. And maybe this is a useful way of looking at the different results to compare which regions have stronger predictability, seasonal predictability patterns. So in this figure, I show the results of the sea ice predictability results for all 6 sectors, the King Haakon, East Antarctic, Ross, Amundsen, Bellingshausen, and Weddell sea sectors. So the top panel have the eastern sectors, King Haakon, East Antarctic, and Ross. And the bottom panel has the western sectors, that is the Amundsen, Bellingshausen Sea, and the Weddell Sea. I know this is quick, but when we compare all of these results, one thing becomes clear that in the eastern sectors, they don't have a prominent summer persistence signal, whereas the western sectors have a strong summer persistence signal. I know that the Ross sector is showing a little bit of persistence here, but I can back this up using the oceanic predictability results. So these are the oceanic predictability results for the same set of sectors, the King Haakon, East Antarctic, and Ross, that's the eastern sectors on the top panel, and then Amundsen, Bellingshausen, and Weddell, that is the western sectors on the bottom panel. So when you compare these two, you can see that there is strong persistence both in the sea ice panels on the top and also in the ice-ocean correlations, that is these negative correlations, which we don't see in the eastern sectors. Now, for the time, I will wrap by showing one more result that is comparing the regional variability to say that whether or not these regions are showing predictability reemergence. All of the sectors show a seasonal loss of predictability and the reemergence of predictability. But they do have variation in when this is happening, that is in the timing. And also there is variation in the strength of it. And also for some regions, it is a little less prominent. And in some other regions, we see this reemergence much clearly in the ocean, whereas the sea ice predictability results might not show that very clearly, which is something to investigate. So I'll wrap my presentation here with some key points. That I was connecting the ice-ocean interaction of the system, the ice-ocean system, to sea ice predictability. And I have to conclude by saying that sea ice predictability is a signature of ice-ocean interaction, and that ice-ocean interaction is closely tied to the local vertical ocean structure and its seasonal evolution, and that different regions around Antarctica produce unique sea ice predictability that is determined by the local ice-ocean interaction. Thank you.
Thanks, Steffi, for your excellent presentation on those ocean sea ice processes and its predictability. And you have a question? Can you please take up that question?
Sure.
How to do the correlation here for the sea ice predictability? Is it a special correlation?
No, this is the total sea ice area. So you calculate the total sea ice area within the regional boundary, and then you calculate that that will be a single value against the single values. So it's the total sea ice area against the total sea ice area in different months. So it's not a spatial correlation. It's after you calculate the total sea ice area for the sea ice. Yeah.
Thanks, Shafi. And
shall I ask one question?
Yes, yeah. Please go ahead. Please go ahead. Yeah. Please.
Yeah, Steffi, a nice presentation. The sea ice predictability and the ocean. You are telling about the east and west. There is a variation in the summer persistence.
Yeah.
What could be the reason for that?
Well, this is quite new results. I have to be honest about that. So as you can see clearly that is present in both the ocean and the sea ice predictability. So one other way we would explain is that the ocean is not able to hold that predictability during that season. So in a way that the ocean predictability is showing that itself is the result to say that they are different. But there's still so much to do, and this is quite preliminary results, and I can't have clear answer at the moment to say.
Okay,
Yeah.
Thank you.
Yeah.
Thanks, Rafi. May I please invite the next speaker, Dr. Bianca Medina, and she will be talking about the drivers of extreme Antarctic sea ice events in summer over the period 1979 to 2022. So
yes,
Bianca, start your presentation. Hi.
First of all, can you hear me? Yes?
Yes, we can hear
Okay.
you. Yeah, share your presentation.
Yeah, I will share it now. Okay, can you see it?
Yes.
Okay, perfect. Thank
Yes,
you.
perfect.
Okay, so thanks for having me. I'm Bianca, and I will present some results from this work that we are doing at the UC Louvain with my colleagues. That it's about extreme sea ice extents in Antarctica during summer. And you might guess maybe where the idea from this work came from, because it's something that has been mentioned several times during this meeting. But in case you missed that, it's the fact that, okay, so this year, Antarctica broke a new record concerning sea ice extent in a negative sense, because it reached a value below 2 million square kilometers. So if you remember Hugues' talks from this morning, from before the beginning of the session, usually, even when we have a seasonal minimum, we should be around 3-4 square million kilometers. So below 2 is really a record. And it's a value that it's even below the previous minimum that was registered in 2017. And on the right, you can see a snapshot of what the sea ice concentration looked like the day that this minimum was reached. That was February 25th. And well, also, you probably know this, but this happened during summer, and now we are in the growing season, but still it looks like 2022 is an extreme year. So we will see what happens. But going back to summer, so of course, this was an unprecedented event that caught a lot of attention, and it's been 6 months now, but we have already quite some studies dealing with this specific event of 2022. So these studies, they really try to characterize the event and dig into the mechanisms leading to this minimum. So maybe it's a bit too late to jump on this train of trying to analyze this year's event. But what we thought to do was to, instead of just considering the separate case studies, we could consider 2022 and 2017 and also the previous extremes and try to do a comprehensive study of these extreme events. And in particular, why not consider also the opposite? So consider maxima and minima in the sea ice extent, because these are mirror events, and maybe we can learn something about the dynamics of extreme events from both of them. So the idea is to do a comprehensive study to try to see if different extreme events have shared features in terms of anomalous patterns in the sea ice concentration, but also in atmospheric circulation, in the ocean, and in other variables, to characterize their timing and persistence. And of course, also trying to understand the role of the different basins, because we know that in Antarctica, we have quite some regional features, and we do not expect all the basins to contribute in the same way to this kind of extreme events. And of course, we are very interested in the physical drivers of these extreme events. So to do that, we use, of course, observations over the period 1980-2022, using some standard products. For the CIS concentration and CIS motion, we used OSISAF and NSIDC, and then ERA 5 for the atmospheric fields. And then we compared our results to some outputs from a model that is the ocean model Niño coupled to the CIS model LIMD, driven by observations from ERA 5. This is also a dataset that has been described by Hugues in his talk previously, well, similar run. Unfortunately, at the moment, we only have the run going until 2021, because we are still running to have 2022, hopefully soon. But still, we have two periods that we can compare. And the idea is that since this is the oceanic model forced by the observations, then if the model is doing good enough, then we expect that it will be able to capture more or less the same extreme events that we have in the observations. So first of all, we need to define what is an extreme event for us. And we just used a very basic definition. So we consider the time series of the standardized CS extent anomalies in JFM. And all the values that exceed 1 standard deviations are maxima, and all the values below 1 standard deviation are minima. So this is what the time series look like in the model and the observations. And I try to highlight all the events that are minima in red and maxima in blue. And if it's a solid line, it represents the observations. If it's a dashed line, it represents the model. So every time that these two lines are overlapping, then this means that there is a match and that the model is capturing the same extreme as the observations. But I understand that it might be a bit confusing to look at the time series. So I try to just summarize this information in the table on the right. So I just put all the years that are detected as maxima and minima in observations and in the models, and the values, the years that are highlighted with the bold font are the years that are shared between observations and model. So we can see that we have a reasonable number of extreme events because, of course, this is a time series of about 40 years. So we have between 7 and 10 extreme events. So this is reasonable. And more or less, the shared events between observation and models are 4 to 5 events. So there are some events that are present in the observations and not in the model, and vice versa. So now with these years, what we do is we build composite maps of the anomalies of several fields to really see what they look like in these extreme years. So we start by having a look at the sea ice concentration. So these are the anomalies in JFM. And on the left, we have the results from the observations. On the right is the model. And on top, we have the minima. And on the bottom, the maxima. This is going to be more or less the same layout in all the figures that you will see. And so it is quite clear that we have two regions that are relevant for both the extremes, which are the Ross Sea and the Weddell Sea. If you focus, for instance, on the first panel, then you can see that there are some negative anomalies. So really a lack of sea ice in the Ross Sea, very evident. And also in the Weddell Sea, particularly close to the sea ice edge. And similarly also in the case of the maxima. The signal in the minima in the Weddell Sea is slightly slightly weaker, but still it's also there. So the results are also comparable between the model and the observations. Then our question is, okay, so where are these anomalies coming from? So first guess, okay, let's blame it on the atmosphere. So we decided to have a look at the anomalies in the atmospheric circulation in the previous season, so in O and D. So these are again composite maps with the same layout as before. And what we can see, and again, it is, I think, clearer in the observations, but still the results are compatible between observation and model. And what we see is that there is definitely something happening with the Amundsen law that is deepened in the case of the minima, and it is weakened in the case of the maxima. And then this is, of course, associated with anomalies in the atmospheric flow. So we have an anomalous flow going towards the continent in the case of the Weddell Sea, and from the continent northward in the case of the Ross Sea. So the question now is, okay, so what is going on in these two sectors? Are they behaving similarly or what? So first of all, well, we went directly from the circulation anomalies to the sea ice motion anomalies, because we expect the wind to be driving the motion of the sea ice. And we are more or less happy to see that we have consistent results. So it's particularly evident again in the first panel, where we can see that the sea ice is really moving away from the continent in the Ross Sea and towards the continent, apparently in the case of the Weddell Sea. But then to further trying to shed light on the mechanisms behind these extremes, we try to also compute the sea ice concentration budget, which is a diagnostic that allows us to decompose the change in the sea ice concentration, that is the term on the left, in three terms. So two terms that represent a dynamical part, which are the advection and the divergence. And these two terms and the change in the sea ice concentration are computed explicitly from the concentration and from the sea ice motion. And then we have a residual part that is, as the name says, computed as the difference between these other terms, that contains everything else, in the sense that it's the thermodynamic part that represents just the melting and the freezing. And then also there are some other parts, such as mechanical redistribution, but the thermodynamical part is really the one that is dominating. So I think that for the sake of time, I will just show you one result that is for the observations and for the minima, but really the message is the same for all cases. And also here I am showing what is going on in the anomalies from October to March. But even if we just, if we analyze the periods separately, like OND and JFM, then the conclusion is the same. And the conclusion is that we do have an anomalous sea ice concentration change, because we have, as we expect, more sea ice loss in the Ross Sea and in the Weddell Sea, which appears to be due mostly to thermodynamic reasons, because you can see that the contribution from the advection and the divergence is really negligible compared to the residual, which is the bottom right panel, which is really dominating. And yes, this is pretty much the same that we see also in the case of the model, even though again with slightly weaker anomalies, and also in the case of the other extreme, which are the maximum. So again, even though we do see some spurious signal, the residual component is always the one that is dominating. So these are somehow our conclusions. So again, the Ross and Weddell Sea are some key regions that have been already highlighted in other studies, and in particular in the ones related to the 2022 study. And we also suggest that the thermodynamical processes may be the dominant one for these extreme events. So that would be it. Thanks a lot for your attention. Happy to take questions if there are any. And if not, just send me an email or just contact me. I will be happy.
Thanks, Bianca, for your interesting talk. It's a wonderful talk on the drivers of extreme sea ice conditions. So I have a question here. Any specific reason for recent extremes of sea ice in 2022? I mean, in June, July 2022, this year, I mean, last month and last to last month?
Sorry, there any specific? Oh, honestly, I don't know, because also this plot is not even mine. So I don't know about the special distribution, honestly. So for the last, I mean, for this, for what is happening now, you mean?
Thanks, Bianca. And next, may I please invite Dr. E. Gop Appel, who will be presenting on enhanced analytical model to estimate sea ice formation in Polynesia, adjacent to Antarctic ice shelves. I could see Igor. Can you please come up?
Speaker is there.
This is live presentation only, no? Not recorded.
No, it is not pre-recorded. I think he is there.
He's there.
Yeah, okay.
And this happens to be the last presentation of this session.
Okay.
Okay.
Igor, IT team, any problem he faces?
No problem.
Okay.
He's there.
Sir, can you hear us?
Yes.
Can the speaker hear us? His camera is also it says on, but there is no feed coming from him. Shall I put him in the attendee and try to get him back? Dr. Igor, can you hear us? Thank you for confirming you can hear us. We can't hear you or see you.
Can you please invite him to start his video?
So his video is already on.
Video and sound also is on.
Yeah, if you see in the panelist, it is already showing on. But I think there is some technical problem on his side. We will try to chat with him and try to figure it out.
Yeah.
Okay. We are before time, right, Jena?
Yes, we have to, because one presentation was when the participant was.
Yeah. So let us wait for Igor to come.
Okay, let me chat with him. I think. Okay. Okay, I think he's not in this meeting.
Okay.
No, he's joining back. Sir.
He was there actually.
But it's showing that he's not available in meeting.
So he'll be joining again.
He'll be joining. Okay, fine.
Dr. Igor, can you hear us now?
I think he is available, but there are some technical glitches, it seems.
Yes. There are some problems with this. Initially, we can hear him like that, but now I don't know.
I think he's trying. Yes.
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 Come.
Mr. Igor, your slides are seen. Please start your presentation. He is able to chat with me, but only the thing is his audio having some problem, it seems.
Initially, we could hear him, but now I don't know. His voice is also not coming.
Slides are also not moving.
IT team, can you please help out if at all from your side it can be done anything?
No, sir, we are not able to talk to him also. And not very responsive on the chat.
We can see it.
And also, Dr. Igor, if you could hear us, we are not able to hear you or see you on the camera. We can see your screen. but we cannot hear you. If you could hear us, can you open up the Zoom, please?
Warmer than today, and it's mostly due to changes in orbital parameters and also PCO2. And we have also just only one ice sheet to go down, and it's a good configuration just to see the changes.
Dr. Igor, can you open up the Zoom bar for us, please? Sir, can one of the conveners drop him an email saying we are not able to hear him or get his video?
Email, is it okay if you are sending now? Sir. We'll wait for Igor maybe 5 to 10 minutes. In case she won't come up, he won't come up, then we'll close the session afterwards. But let us wait for at least 5 to 10 minutes for him. Okay.
Hello. Actually, before Dr. Igor joins with us, I would request all the speakers and the session coordinators to switch on their videos so that we can have a photographic section, and then we'll close the session in case he's not coming up. I would request all the speakers to switch on their videos. So I would request Dr. Sabu to take that photograph.
Yes.
I think only few are there.
Yes, yes. Yes. Done.
Thank you.
Thank you. Thank you. Thanks, coach. I think Igor, he has not come yet. So we'll wait for some time, maybe five minutes.
Yeah.
Yes.
At 5 like that, we can wait, and I don't think he will be able to come back.
Yeah, but he was trying actually, but
Yeah, so maybe some technical problem.
Yes.
Then the solving will take time. So it was a long session. He started by 4:30.
Yes.
Yeah.
Yeah, but we are much ahead of the schedule.
Yes. So after this, another session is there at 8:30.
Yes.
One more session is there.
At what time it is? 3 o'clock it is there? I mean, yeah.
8:30.
8:30 Indian
Yes.
time.
Okay. There is a question here in the chat box. Somebody is asking a question. Could you change my status now? Igor, yeah, then Igor, I think he's trying to come up. IT team, can you please help out Igor? He's trying to join again. IT team, can you help Igor? He's trying to join with us.
Yes, sir. We have already requested him to come to panelist.
Yeah, he has come again. Yeah, yes. Yeah.
Hello?
So, Mr. Igor, audio and video is still not coming.
Can you repeat?
Sir, Mr. Igor's audio and video is still not coming.
Next speaker.
He has sent a message in the chat box. Sorry for problems. I do not think it may sense to you to continue waiting. So, Jena.
Yes.
So what we will do now?
So we should close the session, I think, but he is trying.
He's trying, and he has sent a message in the chat box, no?
Yeah, he has sent a message. He's trying. Could you change my status now? He's just asking to allow actually him, but ID team, I think they are helping him out.
Okay, then we'll wait.
But only the thing is, he's not able to do that. Some problem is there. I think some technical glitches are there.
Okay, we'll wait.
Sir, we suggest you to end the session because I don't think Mr. Igor is able to connect again. He has sent a message that there's no making any sense for waiting for him. He's not able to connect. And we only have 3 attendees left now.
So better, shall we go for closing the session?
Yes, Dr. Jena, I think we can close the session.
Yes. Okay. So, well, with all these interesting presentation, I think he's trying to come up.
Oh, great. So we'll wait.
So we'll wait, yeah, better we'll wait.
I don't think so. We are still not able to hear him or see him.
Dr. Jena, I don't think we can. I think these faces are technical problem. I think so. I think
Let us
close the session. Yeah.
Let us close the session.
Yes, we can close.
So, with all these interesting presentations with speakers from different parts of the world and their cooperation, we have completed this session ahead of the schedule. And once again, on behalf of all the conveners, organizers, we are thankful to the keynote speaker, all participants, technical staffs for successful conducting this session. I would request Dr. Anil Kumar and Dr. P. Sabu, do you like to add anything? If no one has anything else to add, then I think we should close this session.
Yeah, actually, today it was a very nice session and a lot of nice presentations we have seen, especially with the ocean atmospheric feedback in the CAS variability Then Antarctic sea ice extent reconstruction. Then the sea ice simulation, improved understanding about the sea ice simulations. And then the IOD, how the Indian Ocean Dipole is related with the Antarctic sea ice variabilities, and how the Southern Ocean SST is related with the tropical climate variabilities. And the snow petrels as a how the past sea ice conditions, how it can be predicted using this, as well as the new one about the predictability, sea ice predictability also. A lot of talks were there, and new informations we have gathered from here. It's a very informative session, and very happy to attend this session. Thank you for all speakers for attending this session and giving us information about the studies what we are carrying out. Thank you.
Thank you very much. We close the session now.
Okay, so let's close the session now. Okay.
Yes.
Okay.